Testing. 1, 2, 3. Hey everybody. How's it going? Ashley here. Hope everybody's doing okay. I got my coffee. Do you have your coffee? So I got a microphone in front of my face, so I'm hoping the audio is really good. But I have to tell you, I feel strange when I got a microphone in front of my face because everybody's got a microphone these days, right? It's like, this thing. And, today we're going to conduct some business here in relation to a little bit of assembly language. We're going to get our hands on some tooling in Visual Studio, which is actually connected with original SDK stuff, or actually an original product called MASM many decades ago. Has its lineage back then. And there's a lot of other assemblers. MASM is an assembler, Microsoft Macro Assembler. And we're going to touch on that just for the fun of it. But I think getting a little bit of a look at it, might have a little bit of value just to give you a little feeling for how assembly listings are created by hand, because they aren't really listings at that point. It's actually the source code. So how we might write a small little program in assembler and actually compile that, right? We don't use the C compiler in that case. In that case, we use Microsoft's macro assembler. Now there's lots of assemblers, that are available now. There's MASM and many other ones. But we're going to focus on the Microsoft macro assembler because we're going to stick right now with sort of a Windows-centric Visual Studio kind of approach to looking at some of this. And the reason why is I think there's a lot of tutorials for some of the other stuff out there. We're going to maybe touch on some of that other stuff. But today I just thought it might be kind of fun if you still have Visual Studio installed from the last tutorial. It might be just kind of fun to see this a little bit. It might also help you kind of understand that the disassembly that goes on with Ghidra and what you do to help it along is kind of in some sense recreating the assembly source code that somebody might have created by hand if they were authoring the code by hand. Now, obviously these days, a lot of things are written in C and C++ and other languages, and the compilers are generally, crunching that source code, meaning, digesting it, taking it in, parsing it, and outputting machine code, which you can then run on the processor. So today what we're going to do is we're going to write some assembly language directly, and then we're going to assemble it and run the code directly. So we're just going to create a small assembly program and run that directly. And we're just going to look at some things about how that was kind of done. Now, by the way, when you work in some embedded systems like microcontrollers or whatnot, there's still assemblers out there. A lot of those things actually have C compilers that will, create the assembly for you. But sometimes you still do want to work with assembly in certain constructs and whatnot. But I would say with a lot of application development and even operating system source code, a lot of that stuff begins with C or C++ usually. And then from there, it gets compiled and linked and whatnot into the executable. But just keep in mind, it's not like writing assembler is a totally, unheard of thing today, but generally where I see it used is when you have a specific processor like a microcontroller or something like that, and it has some tooling and the instruction set is usually I find a little simpler, a little more straightforward than what you might find with the x86 architecture. The x86 architecture that we use today on our PCs and whatnot has a very elaborate instruction set. It's not that you can't write, code by hand. That was done for decades. But the C compiler and all the build tools, which actually choose the best instructions and, make all those choices for you and whatnot, that stuff is really well done these days. And you rarely have a need to actually go in there and handcraft some assembly. Generally speaking, when you're reverse engineering, that's going to be something that was originally written in C. And you're usually not going to need to know how somebody would handcraft it because nobody ever really did handcraft it. They actually wrote C code, which got compiled and linked, and you're just picking that apart. So we're kind of going to look at what is not done today, but was originally done. And it kind of has a connection to what you see when you disassemble code, when you look at the listing. So back in the day when you would write assembly, you would write the assembly in like a text file or your text editor, and then you'd run the assembler, which would translate the assembly language into machine code. And it itself might link the code or create it directly to something that you could run on the platform, or you might run it through a link stage after you create the object file with the assembler. When specifying the assembler command line to output the machine code or the object code, you might specify assembler listing options. These listing options might create an accompanying LST file, or it could be named anything, TXT or whatnot, but LST was kind of a common extension a long time ago. And that listing file would very much look like a disassembly, like what you might see in Ghidra today, where you see the bytes and you see the addresses and whatnot along with the assembly code. So in a sense, When we look at a disassembly, we're very often looking at what used to be the assembler listing file that you might run when you would actually run the assembler to translate, assembly language into machine code. And that same format you might see also used in debuggers going back many decades, actually. So where you would see the bytes and the addresses and whatnot. And obviously, if you're using a debugger, you're actually seeing addresses live very often. The first debuggers I used, there was no concept of a crash dump, really. You would always be debugging a live target. So today we're going to look at Microsoft's macro assembler, which is hidden in there in Visual Studio. I say hidden, it's not really hidden, but it's there. And a lot of people don't use it directly. Now, while it is documented, the documentation probably, if you have not used it before, you probably would have to search around a little bit to kind of fill in the blanks on how to use it, because the documentation itself kind of shows you features of the assembly language that the Microsoft macro assembler supports, but it's not really like a comprehensive user manual that you would get to have a tutorial to walk you through it. Now, many years ago, when they sold it as a product, Microsoft MASM was the name of the product. They had like a user's guide that would show you certain things that, on how to do things and whatnot. There were other companies that had, assemblers as well too. Borland had one. I think theirs was TASM. Turbo Assembler, that's what it was, TASM. And I think it was meant to be compatible with Microsoft Macro Assembler to some extent. And I think they had some language features they added to there. Microsoft Macro Assembler is part of the build tools, basically. And you'll see it. It's actually there with Visual Studio. We're just going to write a 64-bit, a small little assembler program. All right, with all that said, let's get into it. Okay, so I'm going to search for Visual Studio. We're going to click to download Visual Studio, download Community Edition. If you have Professional or Enterprise installed, that's fine. We're going to go here to install this. Click continue. Okay, terrific. Now I'm going to choose the desktop C++ environment. That's the one that you want. And then just click install. Okay, I'm going to choose skip this for now. We're not going to create an account. I'm going to say dark, and we're going to go Visual C++. All right. Okay, great. Visual Studio is installed. I'm actually just going to exit. Going to exit here. Going to exit here. Okay, so the next thing I want to install is VSCode. So I'm going to go to VSCode here. I'm going to download this. And we're going to run this. And I'm going to accept this there. And then I like to have these checked. So this is not relevant to this tutorial, but when you check these two, you have the right-click options in Explorer to open with VS Code, and that's very convenient. So just FYI. Okay, we're going to say install. And we're not going to launch this. We're just going to click finish. Okay, next we're going to install WinDbg. So don't rush to do this because I want to show you something here. So basically right here, if you take the top link, it'll have this link here. Now this is an app installer file. We're not going to use this. This actually installs a more modern version of WinDbg, just based on my fuzzy knowledge, not actual telemetry or anything like that. Just based on what I have seen, the one that's most in use is the one that's in the debugger tools for Windows download and package, which is part of the WDK, which is the Windows driver kit, as well as the SDK. There are certain advantages to using that particular download and that particular installation. It's not that the more modern experience is not good. It's actually got a nice user interface and whatnot, and it can work for scenarios where you find that it's amiable. I'm going to show you some reasons why I like to use the one that comes with the driver kit as well as the SDK. And so don't take this as a rebuff to the new, more modern one. You can play around with that if you want to. Just keep in mind, don't go and rush and download that one because that's not the one we're going to use. I mean, you could if you want to, that's fine. But if you want to follow along, just watch what I do here. So what we're going to do here is we're actually going to go and look for debugging tools for Windows. Now, I already know the fast way to do this. You don't really have to actually go here. You can actually just go to the SDK and download that. You could actually download the WDK and choose to install the debugging tools. You could actually install them as part of the SDK, but I'm going to show you Visual Studio 2022. When we installed it, it actually installed an SDK for us. So go to the Start menu and type in Add Remove to go to Add Remove Programs. I'm going to expand this. So type in Kit, and you will notice Windows Software Development Kit was installed, and you can see the installation date. That's today because it got installed along with Visual Studio. So Visual Studio's installer installed this Windows Software Development Kit for us. So what we can do is we can click here and click on Modify, and then click Yes to accept the UAC prompt, and then we can click keep change selected. That's the default selection. Click next, and it'll just bring you to the options where we can update the installation of this SDK. Now, don't uncheck anything. Just simply check debugging tools for Windows. And what you'll get is as part of this, and I can actually explain this. I'm going to click change, and it's going to start doing the work right now. So what's going to happen here is it's pulling down the debugging tools for Windows that goes with this particular build of the SDK. Just keep in mind that when you choose to download the debugging tools for Windows with an SDK, you're getting a pretty recent version of the debugging tools, assuming that the SDK that you have installed is fairly recent. And since this is Visual Studio 2022, it's going to install a fairly recent SDK. It may not be yesterday's release, but it's going to be one that's fairly recent. And for our purposes for this tutorial, it's not really highly critical. I'm just mentioning the stuff in case it helps you as you install things in the future. Now, just a little footnote. If I did not have Visual Studio installed and I had no other development products installed and I wanted to install debugging tools for Windows without having to install anything else, all I would have to do is go to download the Windows SDK. So you could just actually search online for Windows SDK and download that. And then when you choose the options that you want to install with the SDK, you would just choose debugging tools for Windows. So we don't need to do that because Visual Studio installed an SDK for us, but just FYI on that. So it's saying here before we use this, check for updates. Okay, so we'll check for updates. Let's go and check and just make sure there's no updates. Okay, there's no updates, so I think we're in good shape. All right, I'm going to close this, and let's close this. Okay, so now I'm going to type Start menu and then WinDbg, and you're going to notice that it's going to have several versions of WinDbg here. So I'm going to right-click on the x64, and then I'm going to choose Open File Location, and you're going to see that it has a shortcut here. So I'm going to right-click on this shortcut, and I'm going to choose Open File Location. And what I want to show you here is there's a folder here called x64. Now, this entire folder here is the debugging tools for x64 or 64-bit debugging tools for Windows, this entire folder. And what's really cool about the, sort of traditional debugging tools for Windows is that it's very developer friendly in that it gives the developer the flexibility to copy the debugger around really flexibly, to use it the way that they want to use it, to really easily find out where it's located, invoke it from the command line, and it provides a lot of little utilities and things that can be useful for different debugging scenarios. We're not going to go into all those for this tutorial, but I just wanted to mention that up front. But I am going to show something here that is something that I do personally. Now, once I install debugging tools, I like to have a copy of it right off the root because sometimes I'm at the command line and I like to type in, C:\/ and some directory and just access the debugging tools and run them. Now, I could put it on the path, but this is just something I like to do. It's because I have a certain workflow that I've used over the years. And if I always know where those debugger tools are, I can create shortcuts or scripts to run various tools in there and whatnot. So this is not something you have to do, but for the tutorial, you may want to do it so you can just follow along. So what I do is I go to the next higher level directory here, and you can see there's other directories for the other copies of the tools. In fact, I can actually just show you. If I go into x86 here, you can kind of see that the same directory structure exists in here. Now, these are the 32-bit version of the tools. And if we go into ARM64, these are the ARM versions of the tools. And you can see there's WinDbg EXE and a very similar set of structure and binary. But these binaries are built for ARM. And if I go here back to where we were at, this is the 64-bit version. And this, again, has a similar structure and there's similar DLLs. There's probably going to be differences when you get to some of the different platforms. So the ARM and the 64-bit may not match exactly. What's really cool about this is we use the SDK's version of the debugger tools for Windows. And that version gave us all the debuggers for all these different platforms. Now it installed them to a default default location. And even though it installed the binaries to a default location, these tools are very flexible. You can copy them where you need to use them. I can put them on a USB drive and copy them to another system, and they'll work right there from that directory. The installer doesn't do a lot of things on the system that are required, like in terms of registry mods and things like that, in order for you to copy these debuggers and use them elsewhere. Like if you copy them on a USB drive to another system, you don't need to like run the installer there, and you can run those tools directly where you copy them. And I don't know, I just like that kind of stuff because it doesn't micromanage me and it gives me the flexibility to do what I want. Is especially with diagnostic tooling, it's just a really positive thing. There's another kit called the Windows Performance Toolkit, and same paradigm. But once you install that thing, you can Xcopy it where you want to Xcopy it. I mean, when I say Xcopy, meaning you can just take that folder, put it on a USB drive, copy that USB drive somewhere else, and you'll have the performance tools with you. So very often developers might have the performance tools and the debugger tools, sort of like on some USB drive, and they just, plug that in where they need to use it and whatnot. And that's something we can get into in other tutorials. But for right now, what I want to show you is I'm going to grab this x64 folder by copying it. So I'm going to choose to copy this. I'm going to go to the root folder here, right? Of C. I'm going to go to the C drive here, and I'm going to copy and paste x64 here. So I've copied x64 here, and what I do is I rename that. Now this is just my thing. I call this debuggers, and then I make it a capital X64, and I just keep that off the root like that. Now all I did was copy that. So the original copy is still where it's located, but I just put a copy off the root because I'm used to accessing it there, and I always just put the latest there. Also, if I update the SDK and it updates the debugger tools to some newer version, won't all of a sudden update the version I'm actively using, which I have copied off to the root when I'm in the middle of a project or something like that, which I personally like because sometimes you might get an update and it might change something with the tools. Usually that doesn't happen, but it can, right? Something can change, and you don't want that to happen when you're like trying to meet a release deadline and you're debugging stuff. If you're using a particular version and that's been working, you kind of want to stick to that. So that's another advantage to being able to copy the debugging tools where you want to copy them. So I might actually even put this to, C debugger, x64 thing, on my path. Today I'm not. I'm just going to use it directly on the command line like that. So now I'm going to open up a command line here. Let's go and open up a terminal window, and I'm actually going to go to our asm directory that we created before. And what I want to just show you is I can type in deb and then hit the tab key. And when I hit the tab key, it'll just complete that for me. And then I can just type in win and tab again, and it'll type in WinDbg, and then I can type in enter, and boom, the debugger will start up. Now, there is a whole lot of parameters. I don't think this has command line help. Yeah, no, it does not. So if you want to know the options, let me just go here. You can type in command line, right? And if I go here, now this help file has been this way for like decades. And even though it's a little bit older in terms of the style of help it is, many developers are familiar with it. So they kind of know how to go here and type in this, and then you can type in like dot to get to like dot commands, and you can click through these or find the one that you want. Very often I will use search. So if I want to see command line for WinDbg, I will type in WinDbg command line. So you can click on here to see use the commands. I'm looking for the one that has the WinDbg command line. So the thing to understand with debugger tools for Windows is that there's actually several debuggers that you get with debugger tools for Windows. Now, those different debuggers are actually sort of the same debugger, but different user interfaces are provided. Now, there's some historical reasons for that. I'm not going to get into those details heavily today. I just wanted to mention that up front. So WinDbg is sort of the GUI version of the interface, and they have some command line interfaces into the debugger as well. And these debuggers share similar command line parameters, but sometimes, but some of them have different parameters. Like WinDbg has some options that the other ones don't have because it's a GUI app, and it provides some features that, might help you design what your GUI is going to look like and how you're going to arrange the windows, and those would not be applicable to the other facades for the debugger. And so the command line options to choose a particular user interface layout wouldn't really apply to those other ones, so they might not have those switches, as an example. But there are many switches which do apply to all the debuggers, and so that's another kind of consistency that you'll find with the tooling here, which is kind of nice. So these are like all the options, and we can type type some of these in at the command line. We're not going to use tons of these, but we may get into some of this stuff as we get into the tutorial. Today, we're only going to really be using WinDbg to quickly look at the output of our assembly, like what gets created by the assembler, but we may get into more of this in subsequent tutorials. Okay, so I'm going to start up VSCode. So I'm going to click here and do new file, and I'm going to say ourprogram.asm. What we're going to do is, one thing we do need to do is I need to exit from this, and I want to type in 2022, and I want to load in x64 native tools command prompt for VS 2022. And then we're going to go to the asm folder, and I want to type in ML64, and we're just going to make sure that that's working. Great. One thing I want to show here is I'm going to type in ML64, and we can do a web search, and you'll see that there is some documentation here. Now, this documentation is something that if you have experience with this assembler, you would use this as a reference. So I'm going to click here and do new file, and I'm going to say ourprogram.asm, and I'm going to just paste in a little shell here of a program, and we're going to talk about this. Okay, so if we go over to the help online for Microsoft Macro Assembler, there is a section here for code.code. And you can see that this actually will indicate the start of a code segment. There are some parameters we can specify on here, but the default is going to be .text, and these are segment names. We're actually not going to get deep into that right now. Let's just go along on the easy path here. But actually, just to make it simple so it doesn't seem like some oblique kind of thing is being, hidden and it's a mystery or something. Essentially, when you are creating a program, when you write a C program and you use the build tools like the compiler and the linker. So let's assume that everything is data on some level. You probably wouldn't say that if you were talking amidst developers, because when you refer to code, you're referring to executable code. But some developers and malware analysis folks and things like that do just kind of look at everything as sort of data. It just so happens that executable code that can run, is data which defines machine instructions which can do something. So if you look at a program like a binary as just, it's a blob of data, but the blob of data has a certain arrangement, and that arrangement, like the operating system, knows how to read an executable file, and it knows within that executable file, what are pre-initialized constant data variables, and it knows how to set those up in memory. It can also identify where code is in the binary, and it can actually relocate that to the right position in the process memory space. And there's a lot of things that go on, and you might say, yeah, the act of the operating system performing loading and relocating things and whatnot, that can become an involved topic simply because there's a lot of things to consider. Not only the fundamentals, but then you can get into security features of the operating system, and some of those security features can, rearrange things in a certain way and whatnot. We're not going to get into all that. Just keep in mind conceptually that a binary, when you build it and the linker creates that final binary that you can then run, within that binary are different sections, and the sections can have names. For example, code can very often be found in a section that has a name .text. You might see a section named .data. There are different section names that are kind of known in different environments. So for example, if you build a binary for the Windows 64-bit environment, you'll tend to see that executable will have certain sections that you would expect it to, have. The names for some of these might seem strange. You might think to yourself, well, why would you have executable code in a section named .text? There are historical reasons for that. I think that's one of the things that can make it seem daunting, even though that's not a particularly complex thing for you to comprehend, right? There's a strange name that's given to a section name that has executable code, and that throws you through a loop for a second because you're like, well, that doesn't make sense to me. That's not what I would have named it. I think part of learning these tools and part of digging into this stuff is actually sloughing that stuff off, not making much of it. I think it's an important attitude to have with some of that. Some things you just have to accept because there's historical reasons, things were named a certain way. And if you get like a deer in headlights when you encounter something like that, you'll only be getting in your own way. So it's best just to kind of look at something like that and, you accept it, you absorb it. I think sometimes learning a little bit about the history of why something got a certain name or how it became to be a certain way can be a very useful thing. And it can also even help you remember some of these things, and whatnot. But sometimes you don't have the luxury to do that, so you just kind of accept it. So I think the simplicity here that I'm pointing out, though, is we're going to create an assembly language program. It's going to be very simple. We're going to build it by assembling it with the Microsoft macro assembler. That's going to call the linker for us. And we're going to pass some parameters to the linker from that command line, and that's going to link it into an executable for us. And then we're going to load that executable into WinDbg to just have a peek at it. And then we're going to add some things to that executable leading up to a point where we're going to have it display a message box. But we're going to start simpler. And with all of this, when we build that executable, it's going to have these sections. And all these sections is a way for the linker to arrange that binary and say, okay, this binary data in the binary is meant to be executable code. And we put it in this section right here. This is constant data, and we're going to put it in this section here. So when you see that kind of stuff, and if any of it looks strange or whatever, just, kind of accept it like, oh, this is a binary that has sections, and each section has data. And the operating system, when it loads the binary, it knows how to read these sections and do things with them to arrange the process space before it hands off execution to the executable code, which is actually part of the binary that's being loaded. If you were to get into actually debugging operating system loader issues and things like that, I mean, some of that stuff can get very hairy. But I also think it's something that's accessible to anybody who has the wherewithal, who wants to dig into that. So what I'm saying is take some of these high level sort of table of contents explanations I give you as a way for you to understand a little bit of this roadmap, and don't be overwhelmed by what you don't know, because even when you know it all in one particular area, you probably don't know it all in that one area, and you certainly don't know all things about all other areas. But I really want to emphasize this because some of these topics, people can mention these things and not explain this kind of stuff, and it can end up, I think for somebody who's kind of learning some of the stuff or diving into it, it can make it seem like there's this whole mysterious thing that's inaccessible. I think some people might have that. And I really just want to emphasize, I don't think that ever goes away, but I think the people who can be successful navigating into different areas don't let that just becomes an attribute of working, generally. So when you approach a space and there's some ambiguity, you don't get overwhelmed by it. You sort of accept like, okay, that has meaning, and you put it into a little box in your mind, and okay, I'll revisit that when I need to or whatever. By developing those chops and having resiliency not to be overwhelmed by details that might not make sense or have historical inconsistencies that might make a lot of sense to veterans in that space, but to somebody new, it's like, well, why is it named this way or something? Part of developing talent, I believe, in this kind of work is actually kind of delving into the acceptance of the idiosyncrasies so they don't overwhelm your thinking, and you can just move past it and kind of focus on what you need to focus on in the moment. And you can always zoom out and kind of, learn something that wasn't so clear up front if you need to do that, right? There's nothing to prevent that. I think in some sense that's very tied to accepting ambiguity and having a talent for accepting ambiguity, and also kind of understanding, deep diving into the ambiguity to kind of make it less ambiguous, to the extent that you can in certain areas. So I think part of it is accepting ambiguity, deep diving to know the details where you need to know them, zooming out to kind of get into some other area that was ambiguous, but you need to make it less ambiguous. I guess on some level, I would say it can be helpful to learn how to resolve ambiguity optimally based on what you're dealing with in the moment. So that way, when you're in the moment and you're interacting with what you're interacting with, you can be resourceful for whatever the context dictates, right? And a code segment that has a funny name shouldn't really be something that blocks you. Just accept it as, well, this is where code goes, and it's got this name, and there's a historical reason why it might have a little funky naming there that just seems odd to somebody who's coming to it new. Anyway, I just wanted to mention that. Hopefully that's not too long of an explanation for something that's kind of minuscule here to what we're doing, but I just thought I'd mention that. What this basically does is it says, hey, here's where our code begins. We see main and proc. So this is the start of a procedure, which you can think of as a function. This is a single procedure assembly program, and all it does is return. And then NP is end procedure, and then end is the end of the assembly file. So if we switch over here to the help, we can actually go and see that there is a definition here for proc. So if we go to proc, okay, so you can see here's proc, and it's got a whole lot of things, that you can, set here, and a lot of parameters and stuff like that. We're not really going to worry about those. And there's lots of explanation, and then you can go down to the bottom here. Well, they don't have a reference to NP here, but they show an example here where they have proc, and then they have NP, but you can actually just go and and click NP right here, and you can see NP right here, and it says marks the end of a procedure name previously begun with the PROC directive. And these are all called directives because they actually are things that direct the assembler during the assembly process. So these are not things like PROC is not something that runs at runtime. It's actually something that the assembler uses at assembly time to direct it to do certain things at that time. What the assembler will do is it will see main and PROC and it goes, oh, okay, well, here's a symbol named main and it points to a procedure that's starting now called main. And oh, here's where that procedure main ends. And we're choosing to put one assembly instruction in there, and that's ret, which is return. So basically the loader is going to load this and then just it will return right when it's called, and that'll be it. Let's actually build this thing. So what we're going to do is go to the command line. So I'm actually just going to copy and paste a command line that I've created here in advance so you can see. And let me just remove this extra space just in case it's confusing. So let's go through these switches really quickly. So /ZI, and in fact, we can actually just do, I'll just do, rem is the comment for the old DOS command prompt, which is what Visual Studio opens up here. So let's just type in ML64 and do help text, and then we can actually see that ZI here will add symbolic debug info. This will allow us to load it in WinDbg and actually have some symbolic information. The next one is the assembly file, our source file that we're going to assemble, and that's ourprogram.asm, and you already know that one. So if I type in ourprogram.asm, there it is. And then we see this link switch here. So if we look in the macro assembler help here for /link, it will show us that these are all options that are passed on to the linker. So ML64 is going to assemble our ASM file, which will turn that into object code machine instructions. And then it will call the linker for us to actually link it into an executable. This is kind of similar to when you run CC or CL, and by default CC and CL will actually, on GNU it'll actually create a.out. That's like a kind of Unix tradition where if you don't name the output executable, it will name it a.out. And that a.out actually gets created by the linker, not the compiler, but the compiler calls the linker for you on your behalf. And so the same thing is here with the macro assembler. If you call it by default, it will actually call the linker for you, and you can pass some options on. So we can look at these options I'm passing. Well, I'm telling link, and we can actually type in link here and look at the help options for link. Now link has a lot of them, so I'm just going to hit enter to go past all of them. You can see that link has a subsystem option here, and you can choose several different subsystems under which you're going to want to run this binary. I mean, you'll choose one, but you have a choice of several. The common ones, for application developer might be console and Windows. Pretty much like console and Windows are, the most used, but I don't know the metrics on it, but console is going to help create a console application, an exe that will use the console for IO and whatnot. And certain things will happen in terms of the operating system performing some housekeeping before it hands off to the executable. We're not going to get into all those, loader and cleanup and resource details relating to, executables and process launching and all that kind of stuff. But just from a high level, when you use the linker to link an object module into like an executable, you want to tell the linker what subsystem in Windows you want to run it under. And if you run it under the console subsystem, you're saying that you want this executable to be prepped when it gets loaded in memory and everything. It's going to be, it'll have certain flags that are set inside of it, like the subsystem flags. So the loader will kind of know certain ways to set that up and load it and all this kind of stuff. And there's a whole lot of stuff involved. Again, that's sort of like high level details. Like we have to pick a path here. So I want to keep it simple, but I do want to touch on some of these things. You just put it in your mind, just keep it as an ambiguous thing. It's just good to get a brush with the linker like this and not have to deep dive into everything, because these can be very complex topics when you get into, what happens with a console app when it's loaded and clean up and all this kind of stuff. And we're just not going to get into all those details today. So I'm going to scroll back up here. And so we can see that we're saying that we want to create a console app. Now entry, if we go to entry, that's here, right here. You can see it's entry and then it says symbol, but it doesn't tell us really what this does. So what we can do is we can go online and we can say MSVC link options. I think that will give us the help. Yeah, linker options. Now this is a great way to learn about these options because the online help for the linker is a very relevant and currently used tool tool. It's not uncommon for a developer to have to, craft a linker command line directly. So the documentation is really kind of good for, seeing what those options do. So if we click here on entry, we can actually learn more about this. We can see when we look at the documentation that this is the start address that, will be called when the executable is loaded, prepped, and ready to run. This will be the start address that it'll be called. What we're doing here is we're specifying a symbol, and the symbol name we're specifying is main. And if you notice, we have our main proc here. So we're just basically saying that this proc is the start address of this console application. /debug. So we'll look at what /debug does. Now, if we look here, it's not going to have much in the way of explanation. So we'll go over to the online help, and you can look /debug, generate debug info. So what this is going to do is this is going to, let's go back up to the command line. It's best to explain it this way. Whenever you build something like a C program or, assemble something like this, you take the thing that works with the source code. So like the C compiler will take the C source code and it will parse it and crunch it and turn it into machine code. And you can tell the C compiler when you're doing that, create debugging info that's associated with that machine code, that object code that you create. Same thing with the assembler. We added this ZI, which actually will create debugging info for the assembled file. But that doesn't mean that that debugging info will be included in the resulting binary, the resulting executable. We actually have to tell the linker that we want it to take any debugging info that's available and to embed it or include it in any kind of debugging info in the output. So with the MSVC build tools, very often that's going to be the PDB file. So loosely speaking here, if I were to diagram this or kind of talk about it while I highlight in the command window here, you can see that this is ML. That's going to run the assembler, and that's going to generate debugging info while it assembles our program, ourprogram.asm. Then it's going to call the linker, and it's going to tell the linker to take any debugging info that was created here and established here for any object modules, and we only have one. It's ourprogram.asm. That's our source program, but an object module will be created from that. And what we're telling the linker is when it turns that object module into an executable, we want it to take any debugging info associated with it and to include it in the final executable debugging output. This will let us start WinDbg or any other debugger, Microsoft Tools debugger for Windows. It will let us start any of those debuggers up with the executable and have that full debugging experience. So it's not enough just simply to put the ZI here. You also have to instruct the linker, hey, for anything that has debugging info, include this. There's also things that the linker can do to actually create a more optimum executable for debugging than otherwise, because the linker can perform some optimizations. So when you create a debug executable with a linker, generally you don't want a lot of those optimizations unless you're debugging an issue that only crops up when there's an optimization in place. Okay, so all those are a little bit off topic for this, but that's just the general gist of what's going on here. Okay, so let's go down to the bottom here to the command line, and let's go get that command line, and let's actually run this. So when we run this, you can see it ran the macro assembler, and it tells us, hey, I'm assembling this program. And then we can see it runs the linker, and it shows us the linker options, and now it's finished. Now, once it's finished, we can actually do dir, and we can see kind of what gets created. Well, we can see it created the object module, okay? But then it also created the final exe and the PDB for debugging. So what we can do now is I can actually run my debugging tools by typing in ourprogram.exe, and it will start the debugger with our program. So right now, what's going to happen is when I start this up, you see it opens up a console window. Now, the reason why that console window is being opened is that the loader has processed this exe on behalf of the debugger. And what has happened is because it's a console app, it has kicked off some of the console infrastructure, if you will, for the process. So now the process actually has a console that it can perform I/O to. Now, one thing you can do with WinDbg, which I like to do here, is I like to actually go and set up an arrangement of windows here. So I like to open up a disassembly window, and then I like to snap that into place. And then I like to open up a registers window here, and I like to put that over here, and then I move this over here like that. I like to get a call stack window, and I pop it down here. Now, this is just something I have done for years, and so I'm just used to this layout. And we'll get more into that. Now, if I want to save this setting that I've just created here, I can actually save this workspace layout. This is called a workspace layout, this kind of design that I just did with the windows. And you can save that in the registry I can just simply click Save Workspace. I can save Workspace as, and it will save it as a named entry in the registry. I can also save the workspace to a file, and I can include that with debugging tools and copy that to like a USB drive or something if I have my favorite layout. So what I'm going to do is I'm going to save the workspace to a file, and I'm going to call this MyDbgWS, and it puts an extension WEW. I just saved it so you can actually see. If I do a dir here, you can see that's my little workspace there. And there's a command line parameter for WinDbg, which will let us run WinDbg and specify that workspace. In fact, if I exit right now, WinDbg, and now I go and rerun this again, you'll see that it'll come up sort of with the same plain default setting, right? What I can do is, well, here, let me run this. I'm just running the debugging tools actually to get the help here. And I'm going to say WinDbg command line. And here are the command line options. And so what we're looking for is workspace. So that's the workspace name. So that's if you save it to the registry. This would be the name that you gave it in the registry. And that's what those non-save to file options do for workspace. I actually very often do use those, but once in a while, I'll save my favorite workspace to a file so that I can load it from a file. So you can load a workspace from a file. Then you can do a save as with one of the registry. So these things, they don't say registry, but essentially it's going to save these workspace definitions in the registry. So if you save workspace as, it's going to save it to the registry. If you do open workspace, you can choose one of the named settings, which is saved in the registry. And that's fine for quick saving on the same machine. But if you go to another machine and you want to use your favorite setup, you might want to have that in a file. And you can actually just say, well, I want to open the workspace from a file, and I can just choose the file here. And then when I choose the file, it's telling me for security reasons, make sure you open it from a trusted source. So I'm going to say okay, and you can see it restored my settings. Once those are restored from file, I can actually just choose Save Workspace As, and then give it a name, and it will save it in the registry on that particular machine. So what you could do is take a workspace file, put it on your USB drive with your X-copied or your directory copied version of the debugger tools, and you could actually just load that workspace from file to have your favorite settings. And then you could do save as to save it on the local machine's registry there. So you just kind of have it there if you just want to have a setup there or something. So there's a lot of different ways to use this. What I want to show you is from the command line. You can also specify. So if I just go and reload this right away, you'll see it's the same plain kind of original setup, but we can actually say -WF, and I can say MyDbg workspace WEW. When we load it up, we're just going to say, okay, we trust it, and it loads everything up, but it also loads up our favorite, settings here. Okay, once this is loaded, we can type in .reload, which kind of resets the symbolic information. It'll unload any, loaded symbols, and it'll do this for all the modules. If I type in LM, we can see a list of the modules, and we can see one of the modules is our program, and more DLLs may load once you start a program, but when you initially load it, it'll always have the actual executable itself, but it'll also have like some of the bare minimal kernel stuff for the OS and whatnot. So one thing you can do is X to look at symbolic information, and we can put a star here to say, I want to look at all symbolic information for our program. And when we do that, we'll see that there's one symbol there, and it's called our program main. So what we could do is I could type in U for unassemble, which is kind of like disassemble, but D is already used as a command in the debugging tools. So U is for like unassemble. I'm going to type in U and hit main, and you can see that here's our program. Here's our procedure. And you can see there's one instruction called ret there, okay? Now, you might be like thinking, well, where are all these commands coming from and, all that kind of thing? Well, you can just go up here to contents, and you can type in like U, and you can see here's unassemble, and it'll tell you can put an address here. So if I put a symbol name here, like our program, bang, and main, that actually gets translated into this address. So if I just take this address directly, and I type in U, and type in the address directly, you'll see it does the same thing, but this address may not be the same address on the next invocation of this exe. So if you're doing some debugging and you keep having to restart the program and you use the symbolic names, it's just going to be easier every time you restart it. Now, a little bit of a commercial here, in a sense, not a commercial for this tutorial or the channel or whatever, but for WinDbg here. Actually, this is the old school WinDbg, but it's tried and true. So very often when you work on different platforms, especially like embedded systems, I've noticed this over the years, the debugging tools sometimes can have little idiosyncrasies, or they may not be the most, flashy UI applications and whatnot. But a key factor is that when you learn the tools on a particular platform, or like WinDbg here, for example, this traditional non-modern WinDbg is a little bit like of an older school Windows application, but it's tried and true, and it has certain features, and it can be very, very powerful for people who know how to use it. The point here is there's tons of commands you can use on the command line. Some of the commands let you peek into what's going on with the OS. Like this is the same debugger that you can use to actually attach to a kernel debugging target. I think what I'm trying to say here is that this might look kind of deceptive, like an old program or something like that, but it is loaded with features. Like there's all kinds of things you can do to dig into little OS internals and peek around at things. Right now, we're not using it for kernel debugging, so we're limited to looking at the process space, but there's a lot of things you can do with that. It can be very helpful to troubleshoot certain problems like with Windows services or things like that. It's used for device driver debugging, with kernel debugging. You can also use it to load a crash dump. These are all different things you can use with these tools. So let me go here to the debugger's x64 folder that I copied to off the root. I want to just show you something really quickly. You see this dbgeng.dll? I should have pointed this out before. This dbgeng.dll is kind of like the debugger. And WinDbg uses that, KD uses that, all those different facades and interfaces. There's a lot of different ways you can communicate with dbgeng. You can actually, it's got an API. You can actually write programs that interact with it directly. So the architecture of the debugger tools, it spans decades, and it might have some things in it that make it seem dated. That's almost by design in some sense, because there's always been an emphasis to make sure things are backward compatible to the point they need to be. You can't just scrap everything and create a brand new set of tools, because there's a lot of complexities with that. When developers are working on an application that they might ship across many different versions of Windows, they really just need tools that work. And, if the tools have a little bit of primitiveness to them, it really is, it almost might even be a benefit, because it might not be using as many, fancy things that might just get in the way of that debugging experience. So seeing older things in the debugging experience is not necessarily a bad thing. And I've actually seen this with other environments too, like embedded systems and whatnot. So just keep that in mind. One thing I wanted to show is another thing here too. You have symsrv. So symsrv.dll contains some symbol management functionality, which you can use to query symbols and things like that. So you could actually write your own debugger by sitting on top of dbgeng and dbgserv. That's basically what WinDbg does. It sits on top of dbgeng and dbgserv, as do some of the other facades that are built on top of dbgeng and dbgserv. And I just thought that would be a nifty thing to point out. I think the point is that these tools span decades. There might be some cruft in there. It might seem a little primitive. They're extraordinarily powerful for debugging things on this platform, both for kernel debugging, user mode debugging, service debugging, crash dump debugging, and all of this stuff is kind of architected around these debugging tools. And so it's just important to keep that in mind. I've used WinDbg for decades. I'm very used to using it. I know I can almost be blindfolded and download the SDK, copy it where I need to copy it. It's not changing, like everything's not changing like, every second, because when you're working on stuff, like you don't need the fanciest UI all the time or whatever. You actually want reliability first, consistency, I would say second, or maybe kind of tied there and first. And then if they want to enhance stuff, okay, fine, enhance it, but take me along too, when you do that. And I think that that's been the spirit, If I could look at it on hindsight, I would say there's always been an emphasis on maintaining that kind of flexibility with debugging tools for Windows. That's why I really like the tools, because when you learn them and you know how to debug problems on Windows by using them, and you almost have to know how to use them, especially if you're going to do some kernel debugging and that kind of thing, it just becomes very powerful to know how to use these tools. Okay, commercial over. Let's go back to the tutorial. All right, I'll close this window. So we've assembled an executable, and it has this one instruction. And what we can do actually, let's set a breakpoint. And the way we do that here is we can say BP and the symbol name. And it doesn't look like anything happened. We can type in BL. By the way, these kind of commands, like operating a debugger, like many years ago, if you go back to the DOS environment, this goes back way back to DOS, like 16-bit Windows. They had a program called Debug. I think originally it was debug.com because they had COM programs, not executable, not EXEs. EXEs were something that came after, allowed relocation and whatnot. Eventually, I think they did have a debug.exe, but that debug program, debug.com and debug.exe, they actually had a command line interface where, it had similar commands like D for dump, these single letter commands and hitting enter. It goes back. Some of that stuff goes way back. I think U did exist for unassemble, to do the disassembly. I think that might have gone back because D was always dump. I'm pretty sure D and DB go back to like debug.com and debug.exe. I'd have to go run those tools. It's been years since I've looked at those tools. But the point here is that, in the spirit of kind of keeping things moving forward, a lot of these command structures, like they have a history, right? They go back. It's kind of similar to Unix. If you look at the history of Unix, there are certain things that have a strange name or some kind of thing or whatever, but there's a rhyme to the reason, right? And people get used to it and they know it. And very often things like that might not change, just simply not to block people and get in their way and let them have the familiar environment that they're used to. Okay, so moving on here. We now see we have a breakpoint. Now, by the way, you can actually open up a window here that will show you your breakpoints. I generally don't do that. I'm so used to using the command line in WinDbg because, when you can use the command line with the debugging tools for Windows, you can kind of fly even in an environment where you don't have the full GUI. And that can be handy for certain kinds of debugging tasks. There are some debugging facades they have like KD and CDB, which actually are all command line driven. And you can actually do a lot of stuff pretty quickly with those things. You get used to not using the GUI for certain things. And so it can be kind of powerful if you learn how to use some of those things and don't need the hand holding of the GUI all the time. Okay, so you can see we listed the breakpoints here and it shows us that there's one breakpoint and it's set on that. So now let's just hit G for go and it's going to run the program. Oh, by the way, before we run the program, you can actually see, and I'm going to type in something here called reload F/F, and that's reload all symbols and do a full reload of all those symbols. Force reload, I think, is F for force reload. So I actually should show you this first. Now, you don't have to do this, but I like to do this. I like to know where my symbols are located. What you can do is I type in MSDL because I know that that's in the URL, so it helps me find the help topic. It's like a little bit of a cheat to find the help topic. And I click on symbol. You can type in symbol path and you can find this article. But if you go down here, you'll find various ways of setting up the symbol path. We're not going to get into that, but there is a Microsoft Symbols server for symbols that Microsoft makes publicly available. And those symbols can be helpful when you want to look at call stacks that have OS modules. So what I like to do is I like to set up a local symbol cache, and I like to then grab this link. So what I do is I include that on the symbol path. So I will actually go to symbol path here, and I'll type in cache for the place where I want to cache symbols locally. And I'll type in C:/sim cache for my cache. In fact, I will put this, for the sake of this example, in the ASM folder that we created so that you can see a fresh version of the cache. And you can read in the help text about cache and stuff like that. We're not going to get into that today. But basically, this is saying that any symbols that are downloaded later on in the path should be copied to this sim cache here. There's a lot of different ways to set up your symbol path. This is just something that I've done over the years. So now I'm copying and pasting that serve star HTTP and then the Microsoft symbol path, and I just paste that in. So what this means is when it loads a publicly available symbol from Microsoft, it's actually going to cache that in my local symbol cache, which is going to be in C:/sim cache. Now this stuff will be saved in the workspace. So I clicked OK. And what I'm going to do is resave my workspace file. So I'm going to say save workspace file, and I'm going to overwrite my old workspace file. And now it will save that information in that workspace file. Now I'm going to reload all symbols. I'm going to force loading. And what it's going to do is it's actually going to go, and for any operating system, symbols, it will load those in. Oh yeah, we did. Okay. So it got PDB symbols for kernel and kernel base and whatnot. So let me actually just go show you these symbols here. So if we go to our folder here, I can type in dir sim cache, and you can see that it created these it downloaded these symbols from Microsoft Symbol Server and it copied them here to our designated symbol cache. This means when we restart the debugging experience again, it's going to actually use the already cached local symbols, so it doesn't have to download those PDBs again. And I can actually do a dir symcache/s, and you can kind of see that it uses these GUIDs to identify unique PDB files. And there's a whole thing to this that you can read. Now, by the way, you remember I could type in contents here to get to the help stuff, and you can actually read about symsrv and all this kind of stuff. All this stuff is very well documented in this help file. I want to show you something else I like about the debugger tools when you actually have it locally copied into a place where you can actually type in something like debuggers, and then you can type in chm, star.chm, and hit tab. So let me do that again. So I typed in the location where the tools are. Remember when I typed in WinDbg to run WinDbg, I did that. What you can do is you can actually type in *chm, which is the help file, and it'll show you the help file. Now I think there's only one help file in there. So it'll bring up debugger.chm, and you can actually just hit enter on that and it will run it from the command line and start up the help. So you actually don't even need the debugger running to open up the help file. So if you ever want to read the help, you can just start that up like that. Again, that's another thing, like developers who use these tools, they kind of just know that stuff. You can also just go to the folder and double click the CHM file as well. And of course, create a shortcut. Okay, so we can see that we got some symbols here. So I can actually type in x kernel 32 bang and then star, and it's going to show me all the symbols that are included in that public symbol file. And you can see there's lots of stuff. These are all functions in the Windows kernel 32 module. Okay, so we have our breakpoint set, which is within our executable in our main program main. Let's actually type in u main. We can see that that's there. Now, what if we want to make this disassembly window point to our main, our main program, so we don't have to look at it only here in the command window? Usually I just type in Control G. So I recommend, similar with Ghidra, you look and you see what the shortcut is, Control G, then you go back down here and click to dismiss the menu, and now you type in Control G, and then you can just paste any address in here or symbol in here, and if it knows about it, it's going to take you there. Boom. Notice it loaded our source file because it knows that we have a source file. It loaded the assembler file in here. Now, the first time that a source file gets loaded, it's going to put the window for source files in some place that it chooses, WinDbg will. What I generally do is I take the source window and I move it up here to where I like it over here on this side. So I like to have my source window here, disassembly window in the center, and then a register window, which is kind of thin. I like to keep it thin kind of over here. I'll widen it up if I need to, but usually I only need to see, a little bit of the register here. They're not that long unless you're going to look at some of these XMM registers and whatnot. But I generally am looking at these, so I don't need that much space here. And then I have my calls down here. Now, in order to save this though, I want to go here and save as to my file. And then I'm going to click save, and yeah, you can go ahead and overwrite it. Okay, so what we see here is we're now doing source level debugging. We haven't gone to this location yet. It's just showing us that we have a breakpoint here. Now, by the way, you can actually set a breakpoint. I just highlight here. You can hit F9. Notice it turned off. I hit F9 again. It turned on again. But very often, if I already know the symbol, I'll just do the BP command that I did and BL, and I'll do a lot of stuff here. I do a lot of things at the command line, the command window here in this line here, and I just memorize some of these things, like F9 is to set a breakpoint and clear a toggle breakpoint. Anyway, we have our breakpoint set. So let's hit G to run, and we hit it. And you can see here, it says breakpoint 0 is hit, meaning we've hit that breakpoint. And you can see here, it shows us there's NtDll, which was calling, into kernel 32. And there's a whole lot of loader stuff that went on to set up our process space and load the executable. And then kernel 32 called our executable at the entry point that we specified on the link command. So if we go back to our command line, we can see that we specified the entry main, and the operating system, has code that's able to see that that's what the executable has set for the entry point. And so that's how the kernel, vis-a-vis NtDll and kernel 32, knows how to call the right address within the binary. So kernel 32 is going to perform loading and stuff, and there's a whole lot of stuff that goes on there. And then it's going to hand off execution to the executable at the entry point that was designated during link time. So you can kind of see a connection there from the build tool to the binary being created. We didn't go over the operating system loader stuff in great detail. It's a very involved kind of thing to discuss. But generally, we have a fuzzy idea that the operating system performs a lot of complex operations to take that binary from disk, figure out, how to set up the process space. But then there's this thing it does after all of that to hand off execution to the binary itself. And all I'm pointing out is that on the link command, we specified an entry point of main, and that's how the kernel loader knows how to call that main address. So it called the main address, and we had set a breakpoint there, so the debugger is stopping at that location. Now, there are certain ways in which you can exit a process cleanly and whatnot. We're just going to simply return to the loader, and it actually takes care of, exiting nicely for us. So we're just going to hit G to run, and the program has ended, and we can see down here at the bottom, you see this NtTerminateProcess. Now, I happen to use this tool quite a bit, so I know when I see that, it has ended the process. And you can see here, here's the stack. You can kind of see that, kernel 32 called NtDLL to terminate the process, and NtDLL has done that for us. And it just shows us sort of this post state here in the debugger of, where things are at after the process ends. All right, so that's kind of, not a very involved program there. So let's try to add something to this program and see if we can make it do something. So I'm going to exit the debugger, and I'm going to go back to the editor here. Okay, so now let's take this another step here, and let's actually put right here, move RAX, 123, okay? Now, what are we doing when we say move RAX 123? Well, remember from the Ghidra video when we talk about the different registers and whatnot. So RAX, it begins with an R, so that's a 64-bit register. EAX, and I can just show you EAX, that's a 32-bit register. And AX is a 16-bit register. And it used to be that you didn't have RAX and you didn't have EAX. Back in the DOS days, you only had AX. So EAX is a 32-bit register, and when they came out with the 32-bit processors, so they had the 16-bit processors, and then they came out with the 32-bit processors, they expanded to allow for 32-bit execution, and in order to accommodate that, they expanded the registers. So AX became EAX for the 32-bit register. And back in the day when you were moving from 16-bit to 32-bit, that was a big deal to have a single register like that, the AX register become, all of a sudden a 32-bit register, which you could do a lot with. Then the 64-bit platforms came out and they expanded the registers further. So EAX got expanded to be RAX for the 64-bit version. Now you can still reference AX and EAX and RAX. So I can say move EAX 123. But what I'm trying to show here by doing move RAX, 123, in fact, actually moving EAX may actually work here just fine because basically the loader is going to look at the return value. Now, as you recall, the return values are in the AX register. So RAX, EAX, or AX, depending on what the caller is going to look at. So if the caller is going to look at only 32 bits, it's going to look at EAX. It's not going to care about the upper 32 bits that are included with RAX. So in order to make that point here, so by the way, a semicolon is a comment in assembler. So let's just draw this out, right? So AX, that's a 16-bit, register, right? That's from the DOS days, right? That's all that existed then, right? Like we didn't have EAX and RAX. So then we had EAX come along when they had the 32-bit platforms come along, right? Now, AX didn't go away, but AX only refers to the lower 16 bits of the 32-bit EAX register. Then the 64-bit platforms came along and they expanded EAX to be RAX. So RAX refers to a full, oops, sorry, I meant to put a hyphen here. So let's put a hyphen here. So the way you can look at this is that the bottom half of EAX is AX. And the bottom half of RAX is EAX. And the top half of RAX is something that only RAX has. That's the top 32 bits, which makes it have 64 bits total. So you might remember from the Ghidra video that return values are returned in the AX register. So that could be RAX, EAX, or AX. So we're going to say move EAX, 123 and return. That means the error code, the return code from this binary is going to be 123 in decimal. All right, so now we're going to verify this. Now this is going to be kind of fun. We're going to actually, well, it might be kind of fun. I don't know. All right, so we're going to actually build the program. Now, you could actually copy this to a batch file or something like that, just so you could just run it. But I have it in the command line history, so I'm just going to, bring it back from the history and just hit enter, and it's going to build our program again. From the history, I'm going to go up here and grab the debugger command line. and I'm going to hit enter. I'm going to say okay. We're going to set a breakpoint here. So I'm going to just highlight there and hit F9, and it's just going to put that there. Now, if I type in BL here to see if that breakpoint was set, you can see actually that that breakpoint was set. So before, what we did, and I can just do it the way we did it before so you can kind of see the differences there, right? So I'm going to clear that breakpoint up there by hitting F9 to toggle it. So we don't have any breakpoints hit. So if I hit VP, that's what we did before. You can kind of see it highlights up here. So just different ways of approaching the same thing via the UI or the debugger commands. The only thing I'll say is if you learn the debugger commands, you can use those across all the debugging tools for Windows debuggers. Okay, so we have our breakpoint set, and what we can do here actually is we can hit G, okay? And when we hit G, we can see that this has, it has stopped here, and it's going to actually load 123 into EAX. So if we type in question mark 0n123, question mark 0n123, you can see that 123 is 7B, and that's confirming the instruction here. We can see that the assembler took decimal 123, and it actually, handled all the conversion to hex for us. We don't even see that that's being done, but you can see underneath it created machine instructions that are loading 7B into EAX, which is the 32-bit version of the RAX register. It's the lower 32 bits. Okay, so what I want to do now is I want to run the T command. The T command is the trace command in the debugger. So I'm going to go here and type in T here. And no, that's not that T. Here's the T, trace command. But you can look at the help text later. I'm just going to explain that T just means advance one instruction. So it's going to run one instruction. So if I type in T right now, it's going to run the move EAX, 7B instruction. So what that means is we should see that 7B moves into the EAX register. So notice that the RAX register, so the RAX register is the 64-bit register. The EAX register is the lower half of that 64 bits. So I want to grab this value out of the RAX register for a second. I want to bring it down here to kind of show you something. RAX currently equals this value here, which is 7FF61C301005. And that basically is a 32-bit value. And there's some non-zero bits set up in the upper 32 bits. So it's basically the RAX register has this value, right? So I'm going to put a little $sign here. So this $sign is a comment, and it just lets me enter in anything I want to. I mean, I can enter in hello, and it'll just ignore the command line. It's a great way to make little notes and things when you're debugging here. Okay, so what I want to show you though is there's a command called R. So I can type in R and hit enter, and that's the register command, and it's going to dump out the registers here. And you can see that like here's RAX, and that matches this value up here. And same with the other registers. Okay, so we're actually going to go now and look at R, and then RAX will show us just the RAX register. And you can see it just shows us just the RAX register. Now you don't need the space there. You can just type in RAX, which is most folks who know the tools will just do that. So the lower 32 bits of the RAX register is the EAX register. So if I type in REAX, we can see it shows us that lower 32 bits of the larger RAX register. By the way, you notice this 123 here? This 123 corresponds to this 123, but as you can see here, the assembler translated that to hexadecimal for us. So we were able to deal with decimal here just fine, but the assembler actually did all the work for us to convert it into hexadecimal. Okay, so that's where the 7B comes from. And there's a little evaluator, kind of like a calculator in a sense, in the debugger tools. So you can type in a question mark. For example, I can type in 1 + 1, and it shows me that that's 2. But you can also type in question mark and then A, and it defaults to hex interpretation of what I enter. So that's going to be a 10. So if I type that in, you can see it shows me, well, A in hex is 10. But if I wanted to actually type in the number 10 like this, that it would look at that as 16 because it's going to look at that as hex. So if I type that in, you can see it's 16. If I want to type in decimal 10, I can put a 0n. That's a nomenclature of the debugging tools. And then I can type in 0n and then 10, and you can see that it interpret that as a decimal 10, which is equal to a hexadecimal. That's not critical right now for the tutorial. Just FYI, you can always do little evaluations, little calculator operations with the question mark, and you can see that all in help in the usual help. Okay. So what I'm going to do is I'm going to type in question mark 1, 2, 3, but I need to put the 0n to say decimal. So 0n 1, 2, 3 is equal to 7b hex. I could also have done it the other way around. I could have looked here and see like, well, oh, there's 7b in the disassembly window there. Let me just type in question mark 7b. Boom, 1, 2, 3. It's just a way, you can do little calculations here and stuff like that. So there's a lot of things you can do with commands like that. I'm just showing you some of the fundamentals there. So now what we're going to do is I'm going to advance one instruction by using the T command. But before I do that, I want to explain something. So what we have here is a small example to illustrate zero extending. What this example does is it loads RAX with -1, which is going to be all Fs or all 1s. So all 64 bits will be set to 1. Then we're going to load 1 in the AL register, which is the lowest 8 bits of the RAX register. Then we're going to load 2 in the second to lowest 8 bits of the RAX register. Then we're going to load 6543 into the lowest 16 bits of the RAX register. And then we're going to load EDCBA 987 into the low 32 bits of the RAX register, because this is EAX. 8-bit register, 8-bit register, 16-bit register, 32-bit register. And these are just numbers that I have incrementing here. So this is 14, 13, 12, 11, 10, 9, 8, 7. This is 6, 5, 4, 3. This is 2, and that's 1. So rather than explain this, let's go right to building this and running it in the debugger so we can just see firsthand. Okay, let's run the debugger. And I'm going to set a breakpoint on the first instruction here. I'm going to enter the G command and press enter, and that'll run to the first breakpoint encountered or to the end of the program if there's no breakpoints. So let's just start by stepping forward. So I'm going to use the P command to step. You can also use F10 in WinDbg. So I'm going to type the P command and hit enter. And you'll notice that RAX got loaded with the 64-bit all Fs here. So all 64 bits are set to 1. You can also see here when we ran the G command, it broke at the breakpoint here and it showed us what the next instruction is. Then we ran the P command to execute that one instruction. You can then type in the R command and RAX and it'll show you what's in RAX, or you can just hit the R key if you want to see all the registers. Let's just stick with RAX right now. So I'm going to do RAX, enter. And you can see that it's all F, all 64 bits are set to 1. Now I'm going to do the P command to step 1 instruction. That's going to load AL with 1. That's the lowest 8 bits of RAX. And you can see up here in the debugger window, there's a 0, 1 there. That's from our move instruction into AL. We can also just recall by using the up arrow, the RAX command in the debugger command line and hit enter. And you'll notice that it has that same value. So now we're going to hit P to step one more time. And I'm just going to type in RAX here and hit enter just to see the results right here in the command window. And we can see, sure enough, it loaded 02 in AH, which is the high 8 bits of the lower 16 bits of the RAX register. And the reason why I just set it that way is because the registers AX, AH, and AL go way back to the 16-bit days before there was any 32-bit or 64-bit processors. So you could actually load AX by loading AL or AH, and you could do various things by using all three of these. So the next instruction is going to load the 16-bit AX register with 6543. So that's going to replace the low 16 bits with 6543 hex. Let me enter the P command and press enter, and then I'm going to type in RAX again. And we can see 6543 has replaced the lower 16 bits of the RAX register. The next instruction is going to load EAX with this 32-bit value. EAX is the low 32 bits of the RAX register. So the next instruction is move EAX, comma, and this 32-bit value. The behavior of this move instruction is going to be slightly different than these other instructions. This move instruction is going to 0 extend because it's moving into a 32-bit register. It's going to 0 the upper 32 bits as part of setting the lower 32 bits. So I'm going to type P and press enter. And now let's look at the RAX register. You can see that the Fs are no longer here. These are no longer set. And if you look up here in the debugger window, you can see only our 32-bit value is set. The reason why is this does not show the 0 padding by default. The rrax command down here in the window does show it. So you can actually see that these are zeroed out here. So you can read about 0 extending and other nuances like 0 extending in the processor manuals. So now what we're going to do is I'm going to advance one instruction by using the T command. But before I do that, I want to explain something. The 7B value, okay, 123 is a 32-bit 7B value, which is going to be loaded into EAX. So basically the instruction we see here is load into the 32-bit register EAX, load in 123 in decimal, which is really 7B. 32 bits is 8 hexadecimal digits, okay, because each of these digits is 4 bits. And basically what we're loading is 00000, 7B into EAX. And so you'd think that RAX up here, and when you look at it in the register, thing, so RAX, you would think that it would have a value of this after the operation. But that's not what's going to happen. It's going to end up having this value here. These are going to become 0. You might say, well, why would those become 0 if I'm only loading something into EAX, which is the lower 32 bits of RAX? So to elaborate, if this is the upper 32 bits of RAX and ECX is the lower 32 bits, and I'm replacing the lower 32 bits with 7B, wouldn't only the lower 32 bits become 7B and the upper 32 bits remain untouched? And no, and that's because of something called 0 extending. The 64-bit processors, they follow a standard, and that standard says that when you're loading something into a 32-bit general purpose register, such as, EAX here, that what you do is you do set EAX, but you end up zeroing out the upper 32 bits, which you're not using. So we're not really using that here. We're only setting the lower 32 bits, but part of the standard is it will zero out the upper 32 bits. And I'm just going to show you that when I do the T command right now. So if we do the T command to load 7B into ECX, look at what happens up here at RAX up here in the window here. So look at what happens up here. So when I hit the T command, you look at what happens up here to this register. I'm going to hit T, and you notice the entire RAX register has now become this value here that I was talking about before, all zeros with 7B at the end. And that's because we only loaded the lower 32 bits with 7B, but the processor itself said, this person's loading the lower 32 bits of the EAX register. That's this standard register here. They're not using the upper 32 bits of the register. So we're just going to zero that out. And that's what happened here. So in a sense, you can kind of look at move EAX, 7B as similar to move RAX, 7B. So now that we have set the RAX register or the EAX register with 7B, and we can actually see that if I type in R here or RAX, we can see it's been set. And if I say REAX, we can see it's been set. R and then just AX, that's the 16-bit. And you can see that the lower 16 bits has 7B. So most of the time people don't look at the AX register like that. Like I very often just do RRAX like that just to look at it, right? Okay, so now that we have set that, let's actually do another trace command. Now when we do this trace command, it's going to run the return command, the ret command, and it's going to return to the caller. Now if you look at the call stack, we are located here in main. When I do T right now, it's going to return back to this caller. Okay, so let's just do that. And we can see that it has returned back to the caller here, which is the kernel. Okay, so you can see here that the kernel is going to move EAX, which is the return value from our main function, and the kernel called our main function after it set up the process. And then our process finished and returned the exit code in EAX. The kernel's going to take EAX, it's going to move it to ECX, and then it's going to call this function RTL exit user thread. Now, If you recall from the Ghidra video, RCX or ECX is the first parameter. So it's RCX is the first parameter, RDX is the second parameter, R8 is the third, and R9 is the fourth. And then the rest would be on the stack. That's like a more advanced discussion. Right now, what this is doing is it's taking the return value from our function and it's moving it into ECX, which is the same thing in a sense as moving it into RCX. It's just moving the lower 32 bits and zeroing the high bits of RCX. So if you actually look at RCX, you can see, does RCX have more than 32 bits? Oh, yes, it does. So you can see this has more than 8 hexadecimal digits, which means that the upper 32 bits of RCX are non-zero. Watch what happens when I trace over where it moves RAX into ECX. It's basically going to set RCX to be 7B. It's going to just copy that over. So let's hit T and hit enter. And you notice RCX now has 7B. Now you might be saying, well, what's the purpose of that? Well, remember the calling conventions. And by the way, the debugger help. Oh, this debugger help is really helpful. If you search for calling convention, here, let me type in AMD64, x64 processor, and then you look at x64 architecture. And if you go down here, it'll have calling conventions. It'll tell you the first 4 integer and pointer parameters are passed in the RCX, RDX, R8, and R9 registers. Now that's similar to the Ghidra video where, you could go to the Microsoft website to see the calling convention there. So the debugger help also provides that because folks debugging stuff are looking at low-level stuff and they're going to need to have cheat sheets to, see what the calling conventions are. So, they're nice enough to keep that stuff maintained here in the documentation. So the first parameter that you would pass to a function would be an RCX. Now let's go look at this function, which is about to be called here by the kernel, which is called RTL exit user thread. Okay, so let's actually go here and type in, I happen to know that this will return a top hit of this website, which is kind of like unofficial, but this is a private like API. Microsoft documents exit thread because that is for public use. This one is not for public use. However, folks out there have documented some of these. And this is not a particularly complex function here. Basically, you can see that it basically takes the exit code for the thread and it takes it as the first parameter, which would be RCX if you were going to call this function. So let's go back over to the debugger. You can see that what happened is the kernel called our main function. Our main function returned the exit code that it desires for the program in the AX register. This is the main thread for the application and it has now returned to the kernel. And what the kernel is going to do is it took that value, that return value we gave it in AX or EEAX, and it moved it to ECX as the first parameter when it calls RTL exit thread. So it's basically the kernel is going to end this thread, and this is the last thread. You can actually go and look at processes and threads, and you can see that this is the only thread running. So when this thread exits, this is the main thread, and this is the exit code. This will be the exit code for the process, basically. What I'm going to do is I'm going to step over the RTL exit user thread, and we'll see what happens. Now you can step over one of two ways. You can hit F10, or you can hit the P command. And again, you can go up here and look at the help and see like the P command. So I can type in P and P step. So you can see P command step is right there, and you can read about that. But this is just going to step over one instruction, one instruction here. So it's going to step over this call instruction. So if we hit the P command, though, we see it doesn't really return from that. It actually just ends up terminating the process. And if we go and look to see the documentation for NtTerminateProcess, so if we go over here and we just open up a window, we can look at terminate process, and we can see that the first parameter is the process handle, and the second one, which would be an RDX, is the exit status. So let's actually dump the registers. So if we dump the registers, you can see that we have -1 for the process, and then we have 7B, which is our return value, which is the exit status for the process. Now, let's verify this from sort of like a a user-friendly, real-world type of, sort of thing, right? Less debugger stuff, right? So let's exit from this, okay? And let's go back to the command line here, and let's actually just run our program directly. Now, before we run it, I'm going to put that as a comment, and I just want to type in echo error level. That's how you can see the exit code for the last process, right? So you can see that error level is 0. That means success. If I type in dir and something which does not exist, that's actually an error. And if we dump that error code, you can see it has error 1. So we know echo error level is a great way of seeing the error code. Now I'm going to go and run our program, and I run our program, and now I'm going to go echo the error level, and you can see it's 1, 2, 3. So we have successfully created a small assembly language program that simply returns the error code 1, 2, 3. In an upcoming part of this video, we discuss shadow space or shadow store, which is part of the x64 ABI calling convention. Before we get to that point in this video, I inserted this overview on shadow store or shadow space. If you're already familiar with x64 shadow space or shadow store, you're welcome to skip this section. Okay, let's click to start Visual Studio. Let's create a new project. Let's select C++, Windows, and then console, and you should see an option here for console app. Click next. I'm going to call this caller, callee, stack usage, debug, release. I'm going to check this box to place the solution and the project in the same directory. It's not critical, but that's what I'm just going to do here. It's fine. And then I'm going to click create. Okay, I already have the code ready, so I'm going to select all and click paste. Okay, there we go. Hey folks, I want to show you this program here because it might help to explain shadow space a little bit more clearly to you. This main function here calls the F1 function, which is right here. Now this F1 function calls this F2 function. Normally it would call the F2 function by making a call this way, but instead it's going to call the F2 function through a function pointer. Just think of pf2 as a variable. It's just like a global variable. So if I were to make a global variable, gi for a global integer, it's the same thing as that, right? Except it's a different type of variable. So this pf2 is a global variable, and instead of it being an integer, instead it's the address of a function that can be called. That's what a function pointer is. So notice by default, we assign this global variable pf2 the address of f2, or to the function f2. What that does is it means that the pf2 variable, by default, when the compiler compiles this and links it, by default at runtime, the global variable pf2, which is a function pointer, will by default point to the f2 function. That means if something uses the pf2 variable to make a function call, by default it will call the f2 function. Now notice there's a volatile keyword. This actually doesn't have to be here. If I remove this, this function pointer will still be defined as a global variable, and it can still be used in the same way. Why do I add this volatile keyword here? Think of the volatile keyword as instructing the compiler, hey compiler, this variable can change asynchronously in ways that you might not be aware of. Now, that kind of indication to the compiler is going to cause the compiler to be very careful about any optimizations near and around that. And so it won't optimize out that variable, and it won't make assumptions about it. So the reason why I'm doing that is I want to show you something with a debug build and a release build. I want to compare the two, and I want to show you the comparison so that you can see the difference between a debug build and a release build. In order for me to do that though, I don't want the compiler to perform some fancy optimization in a release build that will remove this call to the pf2 function. I want the f2 function to remain even in a release build. Now I know this because without that, when I build this in a release build, the compiler performs quite a bit of optimization and pretty much removes all these function calls and kind of does things inline. And that removes the need to create any stacks or perform any calls. So then if I were to show that to you, it really wouldn't be a good comparison to kind of show you the use of shadow space in a debug build versus a release build. So if the compiler optimizes out the call to f2, it pretty much won't need to call anything, and it won't actually have a stack frame or a prologue set up and all that kind of stuff. And we kind of want to see what it does in a release build with F2 versus a debug build with F2. So in order to achieve that, I've used this function pointer and a volatile keyword. Okay, with all that said, let's get back to the program and let's set a breakpoint here on F1 and let's hit F5 to run the debugger. You might have different shortcuts, so just use whatever you need to run the debugger if you are going along with this. And now I'm going to do a right click here and say go to assembly. Now let's look at this. This is the call to the F1 function, and I'd like to look at this in reverse order, and I'd like to jump around from not only this stack frame setup, but here as well, and look at this in reverse order. So basically, we see we have a call to F1. Simple enough, right? And we can see that F1 takes 5 parameters, 1, 2, 3, 4, 5 integers. So the first parameter we know from the Ghidra video, or you can look in the Debugger Tools Help, or look online for the x64 Windows ABI, documentation and calling convention. And you can read about the parameters that are used. But as we know from the Ghidra video, RCX, RDX, R8, and R9 are used for the first 4 parameters when you're calling a function. So we can see that here, right? We can see that RCX is getting 1, and RDX is getting 2, and R8 is getting 3, and R9 is getting 4. Those are the first 4 parameters. Those are the first 4 integers, and those integer values are going directly into those registers before this call is made. Okay, good enough. Where does the 5th parameter go? Well, you can see this is a 5, and that is the 5th parameter. Notice it's going to RSP plus 20, which is 20 hex. That's 32 bytes. So when we call a function, before we call it, there's 2 things that need to be in place. One is the stack needs to be aligned on 16 bytes. That means the stack address has to be a multiple of 16. And we talk about that in this video extensively in a different part. So if you haven't seen that part yet, you'll need to wait until you see that part. And if you've already seen it, then you know what I'm talking about. So when the main function gets called, by definition, it's going to get called with a naturally misaligned stack. The reason why it's misaligned is because it's between 16 bytes. And the reason why it's between 16 bytes is the processor pushes the return address of the caller on the stack as part of calling main. So by the time main receives control, and main receives control at this initial address up here, by the time main receives control, the stack is going to be misaligned by 8 bytes. And that's because the processor pushed the return address of the caller on the stack. That's just part of the agreement. So as part of the prologue code of this function, that is the entry code, the machine instructions that set things up before the core function executes, that prologue code will do a number of things. One, it will realign the stack on a 16-byte boundary. The other thing is it will allocate some space on the stack, maybe for local variables, maybe for other purposes. Also, if the function itself is going to be making other calls to other functions, it itself needs some shadow area, and very often it will include that shadow area in its calculations when it sets up the stack, as happens here, which I will explain right now. So when we enter into this function, this thing pushes RBP to save RBP on the stack. Now, because the stack was misaligned by 8 bytes, this push RBP pushes another 8 bytes on the stack. So after this push RBP, the stack is aligned. But then notice it wants to save RDI, so it does a push RDI. When it does that, the stack address is no longer a multiple of 16 bytes. It's now in the middle of a 16-byte boundary. It came in here, it did a push, which kind of realigned the stack, and then it did another push, which is now, 2 8-byte values, which is 16 bytes. So if you have a misaligned stack and you add 16, you end up with a misaligned stack after. There's nothing bad about that at this point. It's just I'm trying to point out, kind of what's going on. And actually, we could actually run through that. In fact, let me actually stop this and put a breakpoint here at the start of the function, and let's rerun it again from the start of the function. So we're at the entry of the function here. Let me go to the disassembly, and you can see we're at the RBP here. Now let's look at RSP. Here's RSP. Now notice RSP does not end in 0, and this is a hexadecimal value. Now I go into this in detail in the video, so I'm not going to go into this heavily at this exact point with this insert. But keep in mind that if a stack pointer value has an 8 here or a non-zero value, then it's not aligned on 16 bytes. If this has a 0 here, any hexadecimal digit which ends in 0 is a multiple of 16. So the value 16 is 10, and that's a multiple of 16. The value 20 is a multiple of 16. The value 30 is a multiple of 16. The value 38 is not a multiple of 16. That's actually in the middle of 16. That's in the middle of a multiple of 16 in a sense, right? To give you an example in decimal, if I were to say something had to be a multiple of 10, right? Well, 10 is a multiple of 10, 20 is a multiple of 10, 30 is a multiple of 10, 35 is not a multiple of 10. It's in the middle of being a multiple of 10. If you add 5 to 35, you'll have a multiple of 10. I don't want to confuse things by going into decimal, but since decimal is such a familiar number system, sometimes that example might help, right? So hexadecimal, because, because each place in hexadecimal can have up to 16 digits, 0 through F, that second place in hexadecimal is the 16s place. You can think of it as that. So if you have a 0 in the ones place, it basically means you're on a multiple of 16. Same thing in decimal. If I have, 100, I know that's a multiple of 10. If I have 250, I know that's a multiple of 10. If I have 1055, I know that that's not a multiple of 10, but 1050 is and 1060 is. You guys know that as well too. It's very easy to know that when that last digit has a 0, that the number you're looking at is a multiple of whatever the base of the number system is. So for base 10, it's a multiple of 10. Hexadecimal is base 16. So something is a multiple of 16 if that last digit has 0 in it. Okay, so when we enter into this function, we can see that it's misaligned by 8 bytes because there's an 8 there in the last digit. So if I go and hit F10 to step 1 instruction, we can see there's now a 0 there. That's because it pushed RBP, which realigned the stack on a 16-byte boundary, meaning RSP, which is the stack pointer, is got an address, which is a multiple of 16. But then it goes to save RDI with another push. I just hit F10 again, and you can see, well, it's got an 8 there now because it just pushed another register on the stack. That decremented the stack pointer by 8 bytes to accommodate the RDI value, which happened to misalign the stack. The whole point is when we get called, our stack is going to be off by 8 bytes because the processor pushes that return address on the stack. So what this prolog code is doing is it's saving a couple registers. That doesn't realign the stack. Now notice it reserves some area on the stack by performing a subtraction of the stack pointer value. So it says sub from the stack pointer F8, okay? Now F8 includes 8. Now that 8 realigns the stack on a 16-byte boundary. The F0, if I go to calc here, you can see that F0 happens to be 240. So it's reserving 240 bytes, but it's also adding 8 to realign the stack. So in one fell swoop, it's reserving 240 bytes on the stack, and it's realigning the stack on a 16-byte boundary. That might normally be non-obvious, but that's kind of what's going on there. Now we're going to skip ahead these other instructions here, and we're going to jump down to the beginning of where our function call is set up. If we work from the bottom up, so this is a call to the F1 function here, and we can see that the first parameter, which is a value of 1, goes into RCX. The second parameter goes into RDX. The third parameter goes into R8. The fourth parameter goes into R9. And the fifth parameter goes into RSP plus 20. Well, what is that? Well, the first 4 parameters go into those registers RCX, RDX, R8, and R9. Any parameters after those first 4 parameters have to be passed on the stack. And they are passed on the stack after the shadow area. So you're seeing that it's storing the 5th parameter here at RSP plus 20. Well, why RSP plus 20? Why not push it on the stack? Or why not, RSP itself? Why RSP plus 20? Well, because by definition, the shadow area has to follow the return address when the callee gets called. So when the callee gets called, it expects that the first thing on the stack is going to be the return address to the caller. After that, given the x64 Windows ABI and calling convention, the callee expects that after that return address, there's going to be 32 bytes. And those 32 bytes traditionally could be used to store RCX, RDX, R8, and R9, or they can be used as needed by the callee. You might find that debug builds, the callee might store RCX, RDX, R8, and R9. Whereas in release builds, you won't see it use that space. I'm just giving these as examples. You always should probably examine the code to actually see what's actually happening. I'm going to show an example right now where it does just what I mentioned. So as I mentioned, this sub RSP, F8 is subtracting 240 bytes plus 8. That plus 8 is realigning the stack on a 16-byte boundary, which is something we must do before we make a call to another function. At the time we call another function, the stack must be an address, which is a multiple of 16 bytes in order to meet the requirements of the x64 ABI calling convention. This subtraction from RSP of F8 not only includes that 8 bytes for realigning the stack on a 16-byte boundary, but the resulting RSP value itself is the start of the shadow area for any calls which take place in this function. Now you might ask, how do I know that? Nothing here tells me that. Actually, something does tell me that. I know that this is running on Windows. I know that this is meeting the x64 ABI calling convention, the x64 calling convention, which you can read about, and we talked about a little bit in the Ghidra tutorial, and we're talking about it a bit in this tutorial as well. Because it's meeting that calling convention, and because it calls a function here, it calls this function f1, and we know at the time it calls that function f1, it must be meeting the proper setup for the calling convention. And the calling convention requires that caller. We are the caller now. We are main, and we're going to call f1. At the time we call f1, that stack, that RSP value must be an address, which is a multiple of 16 bytes, and it itself must point to the start of an area of 32 bytes, which can be used by the callee as needed, meaning we shouldn't store anything as the caller in that space that we, expect to be there when the call comes back to us. We're basically keeping that space on the stack reserved for the callee. We set it up and ensure that it's there. So it has to be there. So I know by the time the instruction pointer gets to this address, there are two things that need to be in place. The first thing that needs to be in place is that RSP value, the address of the stack, must be a multiple of 16 bytes. The next thing that needs to be in place is that the RSP value itself must point to a 32-byte area that is the shadow area. And I know that when I call that function, the callee, when I call the callee can use that 32-byte area as it wishes. And so because I don't see anything here, there's nothing here doing a subtraction on the stack or setting up additional area on the stack here. The only thing that's doing that is this sub RSP, F8. So because of that, I know that this RSP value must point to the start of the shadow area. That tells me that 32 bytes of this F8 here must be for shadow area. So let's go trace through this here, and we can see that this loads up. We can look down here and you can see that, the RCX register has 1, the RDX register has 2, and R8 has 3, and R4 or R9, R8 has 3 and R9 has 4. Now, if we get the stack pointer, we can do something here. We can grab the stack pointer by right-clicking and let me double click and then right click and do copy of the stack pointer value. And what I'm going to do is open up a memory window here. Now, if you don't have one open, you can go to Debug, Windows, and choose Memory, and then just open one of these. I have this one open. And then I'm going to paste the stack pointer in here and hit Enter. And okay, so we put that in here. Now, what I want to do is set up the columns to be 1, and I want this to be an 8-byte integer. So basically what it's going to show me is one value per line here, one 8-byte value per line. This is the value of RSP. We can see that the value of RSP ends in 0, so it's 16-byte aligned. It is a multiple of 16 bytes. This is the first shadow area, traditionally for the callee to store RCX if it wishes. This is the second shadow area, traditionally for the callee to store RDX if desired. This is the third shadow area, traditionally for the callee to store R8 if it desires. And this is the fourth shadow area for the callee to store R9 if it desires. Now, these 4 shadow areas can be used by the callee as it wishes. Doesn't have to be for RCX, RDX, R8, and R9. Now, here is the first value on the stack after the shadow area. This is RSP plus 0. This is RSP plus 8. This is RSP plus 10 hex. 10 hex is 16. This is RSP plus 18 hex, or 24 bytes. And then this is RSP plus 20, or RSP plus 32 bytes. 20 hex is 32 bytes. And that, you can see that there is a value of 5 here, right? This parameter is an integer, so it's only 32 bits. So that's why it says move dword pointer 5 into RSP plus 20. So you can see here that this parameter is only using the first 32 bits of this stack location. The upper 32 bits hasn't been zeroed out. It actually has some garbage in there. But since the callee has a prototype that says that that's an integer, it's only going to use 32 bits of that value as well, as we will see. Let's hit F11 to trace into the call to F1. And we see there's a little indirection here through a stub. That's not uncommon to see when you're looking at the low level of a build and the internal, construction of things. Let's hit F11 again to jump past this stub. Now this goes to our F1 function. Now we're in the F1 function. Now this is a debug build. Notice in the entry here, it's actually moving C, D, 8, and 9 into these stack locations. What this is actually doing is this is a debug build, so it's loading RCX, RDX, R8, and R8 and R9 into the shadow area. That is one of the ways that the callee, and this is the callee from main. Main called us, so F1 is the callee from the perspective of main. So when main called us, main's return went on the stack, and we can actually verify that. So let's go get the current stack pointer. It should just be one greater than this stack pointer here. So if I go to RSP, we can see that one less because the stack grows down in memory. So we can see it's 38 now instead of 40. So if we go to the memory window here, we can see the last one was 40. So let's actually just pop this in to go to 38. We notice a couple things. First of all, 38 ends with an 8. So we know the stack is misaligned. That's because the caller had it 16-byte aligned, but the processor pushed the caller's return address on the stack as part of the call. And the caller's return address is 8 bytes. Which naturally misaligns the stack. This misalignment is expected by the callee, and the callee will fix that up, just as main as a callee fixed it up, as we just talked about. So this is where the stack currently points to. So if we look here, you can see this is the current stack value, and that's the one that ends in 38. And if we go here, you can see that this is the current stack value. So let's double click on main here to go into main. And if we look, you can see that this address here, the one that ends in 1A4E, matches this address here, 1A4E. So that is the return address. So if we go double clicking at the top of the stack here, so I'm going to double click on that and we go back to where we were. Upon entry to this function, the stack pointer currently points to the return address of the caller, which we expect. And the stack is naturally misaligned by 8 bytes. And it's misaligned by 8 bytes because the caller, in this case main, had the stack perfectly 16-byte aligned, meaning the stack address value was a multiple of 16 bytes. But then it made a call to this function F1, and as part of handling that call, the processor pushed the return address of the caller, which is the address in main that follows the call instruction. The processor pushed that on the stack. As part of pushing it on the stack, it obviously has to decrement the stack value, and since an address is 8 bytes, that naturally misaligns the stack by 8 bytes. This is not a bad misalignment. It's actually expected by the callee, and the callee will adjust the stack accordingly, just as we adjusted it in main when we got called. The top of the main adjusted it to fix that alignment issue. So if we go over here to Notepad for a second, you can see this was the stack pointer at the time that the call was made to this F1 function. So let me double click here on main. When we were on this call to F1, this is where RSP pointed to. Then this call executed and it ended up calling this function. As part of executing that instruction, that call instruction, the processor took this address and it actually pushed this on the stack. So this became main as caller return address. Okay. And then all these need to change because the offsets are different now because, so we would say 10, 18, 20, and 28. So let's go back to this. Okay, we are already on this function. So at the top of F1 here, this is what the stack looks like. RSP points to the return address in main. So when the F1 functions, executes the ret instruction, this address will be popped off the stack so execution can continue in main at that location. When the processor pushed this address on the stack, the shadow area is at the stack location plus 8 bytes. So RSP plus 8 is the first shadow location. So if we look here, we can see that in this debug build, F1 stores C, D, 8, and 9 in each of those shadow locations. This is a debug build, so it's likely doing this to help with any kind of debugging that goes on, because these registers will be reused for subsequent calls. And by storing them here, if you break into the debugger and look at things, you'll be able to see what the values were for those parameters at the time this call was made. If these values were not saved, you wouldn't be able to see what they were when this function was called. And if you're looking at a debugger, well, it's nested deep into a bunch of calls, and you go look on the call stack at an earlier time, you may not be able to know what the parameters were because they'll be wiped out. But because they're being saved here, it helps with the debugging, process. Now, what we're going to see is that in a release build, this is not present. So you can also see, though, it's storing C in RSP plus 8 and D in RSP plus 10 and so on and so forth. And we can see that that's correct. RSP plus 8 is the first shadow location, and RSP plus 10 is the next one, and so on and so forth. The fifth parameter, by the way, is way up here at RSP plus 28. And that is what the x64 ABI and the calling convention defines, is that upon a call, the shadow area is going to be 8 bytes past the return address of the caller. Okay, let's go back over here. Okay, so let's actually trace this. I'm going to hit F10 to go past all these. Now, you can see it just pushed RBP, and that actually ends up aligning the stack, because remember, the stack is off by 8 bytes. Anytime you push, you decrement the stack by 8 bytes. So the stack was misaligned, and in the middle of a 16-byte area, we just pushed a value. So that makes the stack pointer a multiple of 16 bytes, and we can actually see that by looking here in the register. You can see that ends in 0. You can see that the RSP value ends in 0. That means it's a multiple of 16. But then it goes and pushes another value, which is going to subtract another 8 bytes, and now the stack is misaligned again. But then you'll notice there's a similar subtraction from the stack here of F8, and you'll notice that 8 there. That 8 there is going to cause the stack to realign on a 16-byte boundary. And so when we run this, you can see that it ran that, and that now the stack pointer ends in a 0. It also has F0 bytes there, which is 240 bytes of extra data there that it's reserving on the stack. As with the main function, we know the initial 32 bytes starting at RSP right now is shadow space for any calls that this function makes, and we know that by looking later on in the function, as we'll see right now. So we're going to trace through here. You will notice that this thing is loading the PF2 function pointer into RAX, and you'll notice down here it calls RAX, and that's how it calls a function pointer. So it's pretty simple. It's basically loading the address that this pointer contains, because a pointer contains an address. Basically, it's a variable like an integer, but instead of being an integer, it's an address. Addresses are kind of similar to integers usually on most platforms. They happen to have a certain size. So on 64 bits, an address happens to be 64 bits or 8 bytes. That's different than a 32-bit integer. So when I use integer in this context, I mean it kind of loosely. So maybe I should say integral. But typically addresses are very often unsigned integers of the magnitude of the platform. So in this case, the magnitude is 64 bits, right? So addresses are going to be 64 bits here. But when you get to a low level like this and you're dealing with the bits and the bytes, what you see here is that this is a move instruction, which is loading the RAX register with the value that is in PF2. And PF2 is just simply an address. And that PF2 address is being loaded into the RAX register. If I actually trace past this and we look, we see that RAX got loaded with something. Well, actually, let's actually see what this address is. It's 117C. I'm just using the last 4 digits there because most of these other digits are the same. So if we can just see that it's 117C. Okay, so what I'm going to do is I'm going to right click on this address that's in RAX, and I'm going to put it up here in this address box up here, and I'm going to hit enter. Oh, I think I might need to put 0x here. Let me try that. Yeah. So this actually shows us it's a stub to F2. So let's grab the address that the stub calls. So I'm going to put a 0x here and get rid of that H and hit enter. And that brings us to F2. And we can see that this RAX has been loaded with the address of F2. Here, let me actually just go. Okay, let me right click here and do show disassembly. Okay, now we're back. So basically, the RAX register just got loaded with whatever was in the PF2 global variable. The PF2 global variable is a function pointer. That function pointer at this point in time happens to be holding the address of the F2 function. And we just verified that, in fact, RAX contains the address of the F2 function. Under the covers, we can see it actually holds the address to a jump instruction that jumps to the F2 instruction. That's like some internal stub that's been set up. But effectively, if you call the RAX, the address in the RAX register, you will end up calling the F2 function. And that's what happens down here. You can see a call to RAX. So we already know we are preparing to call the function that is pointed to by the PF2 function pointer. And all this other stuff between those two instructions, so this one's loading the address in RAX, and this one's going to call F2. It's actually going to call the PF2 function pointer. That function pointer has been loaded into the RAX register. So effectively, this call of RAX is going to call the address value that was in the PF2 variable. All the rest of this stuff in between is really the setup of the parameters. So let's look at this from the bottom up. So ECX is loading dword pointer A. Now it's using symbols here. So I'm going to right click and say, don't use symbol names. I'm actually going to get rid of that. And you'll see it changes those symbols to actually be what's really going on with the machine instructions. So we can see that A is located at RBP plus E0. So I'm actually going to expand this, make it a little bit bigger here. Okay, so we can see, and if we flip back and forth, so if I go to show symbol names, you can see this is A, B, C, D, right? And then this is E. So if we right click here and we say, and by the way, E is the fifth parameter, and notice how it's setting that fifth parameter up in the same area just past the shadow space, right? So it loads that fifth parameter into ECX, and then it loads it into our shadow space, because when we call PF2, which is really the F2 function, it's just pretty much the same setup that main had to call us, because both the function signatures are identical. They each have 5 integer parameters, and that fifth parameter is one greater than those initial 4 registers, which can be used given the x64 calling convention. And any extra parameters like that need to be passed on the stack after the shadow area. So this is loading E from just past the shadow area of main's call to us. It's loading that in, and it's going into ECX. And then this is going to take ECX and it's going to store it in our area just after the shadow area. So our shadow area, meaning F1's shadow area that it sets up for F2 to use as F2 wishes to use it. That's something that we're setting up on our stack, and our RSP value is pointing to the start of that shadow area. So 32 bytes after that shadow area would be for the fifth parameter, and that's what's going on when ECX is saved in RSP plus 20. It's actually saving this in one past the shadow area. That's the fifth argument. It's the same thing that happened in main. So we know that A is being loaded from where it was saved when we entered our function, because that's the only area where it was saved that our function here, this F1 function, knows about. If I right click here and I turn off symbol names, you can see that this is like E0. This is actually E8, which is plus 8. This is F0, which is plus 16 from this E0 value, right? And this is plus 24 from this E0 value. And these values here, these 4 values here correspond to these 4 values. So on entry to this function, these are being saved at these locations. RBP gets set up with RSP plus 30 after RSP is subtracted with F8. So there's a bunch of math that goes on here such that RBP plus E0 effectively equals what RSP plus 8 equals here. So if you take the time to do the math, you'll see how that matches up. We're not going to do that here. We're just going to continue to move forward because I want to get to F2 to kind of show you what goes on there. So we're going to step through all this, and you can kind of see that the registers are being loaded. So RCX has a 1, RDX has a 2, R8 has a 3, R9 has a 4, and we already know that RSP plus 20, which is one past the shadow area, contains the number 5. And we could actually look at that if we wanted to. So if we go and look at registers here, and I get the current stack pointer, So we're going to get the current stack pointer, and I'm going to pop that in there, and we can see that this is plus 0. This is plus 8, this is plus 10, and I'm talking hex here, so 10 is 16. So in decimal, this is plus 0, this is plus 8, this is plus 10 hex or 16 decimal, this is plus 18 hex or 24 decimal. And notice here, this is the 32-bit value of 5 that was moved into the area past the shadow space right here by this instruction here. Now, this call instruction is going to execute. The stack pointer is going to decrement by 8 because the return address, which is going to be this address, 19D0, is going to get pushed onto the stack by this call instruction. That's so when the function that's called, when its ret instruction executes, it's going to pop that address off the stack so that execution comes back and continues here. That's the same thing that happened, in relation to main calling this function. So we're going to hit F11 to trace into this function, and here's this little stub. I'm just going to hit F11 again, and we're at the top of another stack. And you can kind of see here that it's doing the same thing. It's saving all the registers that we were called with, right? C, D, 8, and 9 in the shadow area that was provided by the caller. So this is F2, the callee, using the shadow space that F1 allocated for it as it wishes, and in this case it's using it in a fairly standard way where registers CD 8 and 9 are being stored in the shadow space number 1 through 4 accordingly, each one being 8 bytes. So we will trace through all these. This is going to do the same thing. Push. It's going to subtract 108. Notice that little 8 after. That will cause the stack to be aligned. So if we look at the stack pointer right now, it ends with an 8. We know that that's not a multiple of 16 bytes, so it's not 16 byte aligned. After this sub instruction, watch, it will be aligned. This sub instruction executes. Notice that the stack pointer ends with 0. That means it's aligned on a 16 byte multiple, which means it's 16 byte aligned. It needs to be 16 byte aligned before this function makes any calls to another function. Generally speaking, you'll see the prologue or that entry code of a function fix up everything with the stack as needed before executing the core part of the function, and part of that will be to make sure that the stack is aligned on a 16 byte boundary so that everything is ready in case any function calls are made. As we've also seen, this entry code also performs some subtraction on the stack pointer, which effectively allocates some space. And we've also noticed that at least in this program, it's very common for that stack pointer to be pointing at what is the shadow space that any callees can use that our current function ends up calling. So this function will actually be calling, it'll be calling count here, and count actually has the same requirements. It will need to, have that shadow space existing and all that kind of stuff. So basically we're just going to skip down here to where it performs all the math, and we can actually see that it's going to load in the various values. And in fact, if we right click and we do symbol names, you can see that it's actually going to load these values from the places where it saved it in the shadow area. So it's going to load EAX with the value of 2, and it's going to load ECX with the value of 1. So that's A and B. Now it's going to add those two together and save that value in ECX. So we can see that C has 3. That's 1 plus 2, 3. Then it's going to save that value that it just added together, that ECX is going to save it in AX. Now it's going to add the C value to AX. So the C value is going to be, that's going to be 1, 2, 3. So that'll be 3 plus 3 should be 6. And so EAX should have 6, and it does. If you look down here, it has 6. And then it's going to add D. Okay, so we can see that it gets 10, the value 10. And then it's going to add the number 5 to 10. That should be F, and that is F right there. And again, you can right click here and turn off symbol names, and you can actually see these stack locations that it's using to get these values. And these stack locations correspond to the shadow area where it saved these registers upon entry. What we're leading up to here is to see how this changes in a release build. Okay, so I could call count right here and go through all this. We don't need to do that. I'm going to hit stop to stop debugging, and I'm going to choose release build. And then I'm going to set the same breakpoint, and I'm going to hit F5 to build and go. We are going to hit right click and go to disassembly. Now, because this is a release build, it's going to be it's going to be optimized compared to the debug build. So what you'll notice here is the source code shows that we call F1, but you'll notice that it actually, the compiler has optimized out the call to F1. So let's take this one step at a time. First, we notice that we're subtracting from the stack 38. Now we'll notice that this is a smaller value than it was in the debug build, so it's using less space. And we notice that it's 38, and that's higher than 32 bytes. So we know that there's shadow area included in this subtraction from the stack area. So this sub RSP, 38 both aligns the stack on a 16 byte boundary, and it allocates shadow area for any calls that this function makes. Now notice here that RAX is being loaded with the PF2 function pointer. Well, wait a second, we're in main. Why would this be accessing the PF2 pointer here? Well, the compiler was smart enough to see that this function, f1, doesn't really do much. It simply calls this function pointer. So the compiler decided to omit this function, f1, because it's not needed. And so it decided to change this call here effectively to be this call here. So essentially main has kind of become the f1 function itself, in that it itself is going to directly call the PF2 function pointer. Main is still main, and the f1 function has been optimized out. Main now has the job of doing what f1 used to do, which is to call the PF2 function pointer. Okay, so I'm going to trace down into here, and we can see that RAX loads with the PF2 function pointer. We're not going to go and double check that. I know that that's going to be the F2 function pointer. But you can check it yourself if you want to, if you go through these steps yourself. So the next thing we see here is that D is being loaded with 2. And D being loaded with 2 makes sense, right? Because C would get 1, D would get 2, 8 would get 3, 9 would get 4, and then that fifth parameter gets stored after the shadow area, as we've discussed. So we see that again here. Here's the shadow area, and that fifth parameter gets passed 1 past the shadow area. So that's the shadow area plus 32 bytes. That's where that fifth parameter gets stored. And that's the same, that's what we saw before, and it's the same thing here. You can see that this is the fifth parameter, it's number 5, and it's being stored at RSP plus 20. Well, RSP is the start of the shadow area. RSP plus 20, which is 20 hex, which is 32 bytes. So RSP plus 20 is 32 bytes after the start of the shadow area, or it's the first address after the shadow area, and that's where that value 5 is going to be stored. That's the fifth argument. Notice what happens here on the next instructions to load up 9, 8, C. Basically, it's doing a little trick here. It's actually loading the effective address of RDX plus 2 plus 1 and minus 1. Remember that load effective address actually loads the address that's calculated by looking at this portion of the assembly instruction. So the assembly instruction is accessing this address, or it wants to access the value of this address, whatever the calculation of this address is. This address is going to be whatever RDX is plus 2. Well, RDX is going to contain the number 2. So what is 2 plus 2? Well, 2 plus 2 is 4. And so it's going to load into R9 the value 4. And what is 2 plus 1? Well, 2 plus 1 is 3. And so it's going to load R8D with the value 3. And what is 2 minus 1? 2 minus 1 is 1. So it's going to load C with 1. So what you can see here is the compiler is using load effective address, not really with real addresses. It's actually using it to just perform some math here, some addition. So let's trace through these. You can see R9 gets a value 4, you can see R8 gets a value 3, and you can see ECX gets a value 1. Now you might ask, why isn't it doing the add instructions that we saw before, or moving the values directly, and why is it doing this using LEA? This is the optimized version of code, and the compiler's made a decision that this can be more efficient. And for the various cases where it can be more efficient, or how it can be more efficient, you can actually search online for, why does compiler optimize using LEA for arithmetic, for example. The goal here of this tutorial is just to kind of show a comparison of optimized build versus debug build, but some of those more finer points or something, you can actually go and read up a little bit about it. A little off topic for this particular tutorial. So at this point, RAX has the PF2 value, the function pointer value, which is the address of the F2 function. And if I hit F11 to trace into where this is going to call, it's basically going to push this return address on the stack. And in fact, let's set up the memory window by grabbing the RSP value. So I will double click to highlight, copy, go to memory, paste this in, hit enter. And what we're going to see is the RSP value is going to change from D0 to D0 minus 8. And let me see, can I do minus 8 here? Will it resolve that for me? Yes, it does. Okay, great. So the stack pointer currently points here. Notice this is the next available stack space. So when we execute this call instruction, the processor is going to push the return address, which is this address, into this location here, and the stack pointer will be adjusted to point here as part of the call instruction. So let's hit F11 to see that happen. And there we go. We did that, and we can see here is that return address, and that address ends with 1065. So actually, let me double click one up on the stack here, and we can see that 1065 is the return address after that call instruction. Okay, so now let's double click on the top of the stack here. We're back here. So now you can see we're in F2. This is a release build of the F2 function. Notice how in this release build of the F2 function, we don't really save any of the registers in the shadow space. And from what we can see, the shadow space is not really being used. But let's follow this through. So the first thing is the stack is set up. Notice there's this little 8 here. That realigns the stack address to be a multiple of 16 bytes, which we refer to as aligned on a 16-byte boundary. Let's step past that. So we notice on entry to this function, there's an 8 here for alignment, and then there's 32 bytes for that shadow space, and that shadow space should be aligned. So now we know after that sub instruction, the RSP value is a multiple of 16 bytes, and it itself at this point represents the start of the shadow area. So we can actually verify that. Let's go to the registers here, and we can actually see that this register RSP, it has a 0 at the end, so it is 16-byte aligned. We can actually pop this over here. There's nothing really to look at right now. What we know is this is the first shadow area. This is the second one, the third one, the fourth one. This is the extra 8 bytes to align the stack. And this one right here, this 1065, is that return address to our function that called this function. And this 1065 is the return address to the caller of this F2 function. So you can kind of see that sub instruction sort of set things up, and this is our shadow area for this function. And this is just sort of an extra 8 bytes to align things. So clearly though, that the 32 bytes here has to be shadow space because F2 does make calls. Let's go to the register window here, and we can see that ECX includes the 1 that was passed to us, and EDX includes the 2 that was passed to us. Those are the first 2 parameters. And we can see that this is the main calculation that this function performs. It basically adds all these values together, and we can see that it's adding the first 2 parameters together here. The result of that addition will go into DX, so we should see a 3 in DX, and I hit F10 to step 1, and we can see that RDX has 3. So you can see RCX is being loaded with the count object here, and that's going to be passed to the insertion operator for this call down here. So what you can see is some interleaving here. It's actually preparing for a subsequent call, but it's still actually afterwards it's going to continue doing the arithmetic for this statement. So in a release build, you should be prepared to notice things like that. Not everything will happen in a perfect order. You'll see some things being set up for a call later on, and then sprinkled between some of that, you'll see some stuff going on that might have to do with a source code line that occurred earlier. And we see a little bit of that here. So here we saw one portion of the arithmetic, then we saw RCX being loaded with count. Now the arithmetic is continuing. RDX is going to be added to the third parameter, which is R8. So R8, that would be containing a 3, right? So R8 contains a 3. We're going to add RDX to R8, and that's going to be 3 plus 3. So we'll have 6 in RDX after this instruction. So I'm going to hit F10. And then there's our 6. So this addition here is happening one step at a time, and it's accumulating so far in RDX. So now we're going to hit F10 again, and we're going to see that R9 has 4, and we're going to add 4 to 6. And that's going to result in 10 being in EDX. So let's hit F10, and we can see EDX has 10. That's A in hex, which is 10. Next is the 5th parameter, which is a little trickier, right? Because it's not passed in a register, but it's not that tricky. So we can see that EDX, which is the accumulating register right now, right? That's accumulating the total for this addition up here, right? So the first portion of this addition happened here. Then the compiler decided it wanted to insert some setup here for a call that's going to happen later on. Then the compiler decided to continue accumulating the addition that's, indicated by this line. It's continuing that addition here in these subsequent instructions. So this added D and C together. This added D to 8, and this adds D to 9, and this is going to add D to that 5th argument, which is 8 bytes after the shadow area set up by the caller to this function f2. It shows it to us nicely as a symbol, but if we right-click on this and turn off symbol names, we can see right here that it's RSP plus 50, and we can actually kind of do a calculation on that, right? So we know that we got called here, and this did an RSP minus 28. So let's actually go over here to Notepad for a second, and let's actually, I'm going to start with a new one here. Okay, so when main calls F2, stack looks like this, right? So this is higher up on the stack, earlier in the stack, and this is a lower address at the stack, and RSP equals this at the time, just before the call is processed, is executed by the processor. Okay? So what we see is that when we called F2, at the time we called F2, RSP pointed to the start of the shadow space, and 32 bytes after the shadow space was the 5th parameter. Okay. All right, good enough. Okay, so, and let's just assume that any line that we have here is 8 bytes. Okay, so this is 8 bytes, that's 8 bytes, that's 8 bytes, and that's 8 bytes, and so forth. Okay, so the call, so main calls F2. Okay, and when that happens, the processor will push main return address pushed. So that goes on the stack, and RSP is pointing to that. Let's do this actually instead, and we're going to remove this. Okay, and then so this is where the stack points to right when we enter into F2. Okay, upon entry to F2. Then F2 does a sub, and I'll put this out here. So it does, oh, sorry. Oh, come on. All right, so then F2 does a sub RSP, 20. This is to realign the stack and reserve shadow area for calls from F2. Okay? And so when it does that, we have 8 bytes, 8 bytes for a line. And then we have shadow 4. Here, I can just actually grab these and put these here. And then we have the shadow areas that F2 reserves for the functions that it's going to call. So now let's go back here, and we see that it's getting the 5th parameter from RSP plus 50. So RSP currently points to here. Okay, that's where it currently points. So this is plus 0 hex, and I'll just put H there. This is plus 08H. This is plus 10H. This is plus 18H. This is plus 20H. This is plus 28H. This is plus 30H, 38H, 40H, 48H, and 50H. And that is why its addition here, this add to EDX, is adding the 5th argument by referencing RSP plus 50. Because it's referencing the parameter as it was passed to us by main. And because this was the 5th argument, it was passed by main to this F2 function via that stack area that follows right after the shadow area. What we're going to see here is EDX is going to be added to the value of 5. And we could actually see that. So if I go into the memory window here and I type in RSP plus 50H and I hit enter, you can kind of see it brings me to this location where that 5th parameter is right there. You can see the 5 right there. And notice here, it's using D-word pointer RSP plus 50. So if there were garbage in the higher 32 bits, this would actually end up ignoring that garbage. It's just focusing on the lower 32 bits that's located at RSP plus 50. Okay, so after it does that, the EDX register, which is accumulating the addition, should go from 10 to 10 plus 5, which will be 15. And then it goes immediately, and we can actually activate symbols here so that we can see here that this call is calling the insertion operator, and it's passing count as RCX, and the second parameter, RDX, is tote, which is 15. So you can see kind of the elegance here is that the compiler optimized things. Number one, it didn't use the shadow area because it's optimizing in a release build. So it's sort of the philosophy there is we don't need to save things for debugging purposes because this is a release build. So we're going to try to be optimum. And when you save things to shadow area, that's like writing to memory and stuff. It's much slower. So when the compiler tries to optimize for speed, it really is going to try to keep things in the registers as much as possible. It's going to try to limit how much memory it has to access in terms of saving or loading wherever possible. So we can see the elegance of this optimization here as the compiler decides, well, I'm going to need to pass this total value as a parameter down here as the RDX parameter. So because of that, it decides, well, let me use EDX as the accumulator because I'll basically add everything and it'll be in EDX and it'll be ready to go as the second parameter to that call to the insertion operator. So the way you can kind of briefly look at this is this function gets called, the stack gets adjusted, the function, the instructions then will add a total value into EDX. It also sets up RCX with the first parameter to this call. By the time all the values are added together, all the parameters are already set up and ready for this call. And then it just needs to call this, which should output the value. And we step over that with F10. And then we go to our output and we can see that it outputs that value. So anyway, the main goal here was to kind of show you a comparison of release and debug builds. So one thing you could do is you could try taking the volatile keyword off, or you could try even removing that function pointer altogether and looking at the release build. And you'll kind of see what I mean is it sort of removes, all this stuff out. So you can't actually see a release build of the called function because the optimizer does such a good job. It actually removes the F2 function. But in reality, when you have a large program, the compiler can't remove all the functions. So some of the functions will be in there and they won't be using the shadow space, even though the shadow space has been allocated. So the shadow space always has to be allocated by the caller. The callee can use the shadow space how it wishes. And I would just say, generally speaking, never make assumptions about how the shadow space is used. Maybe get a debugger or a disassembler to peek to see what the compiler did in terms of how it actually ended up using the shadow space for any given compiler build tools, situation that you're looking at. All right, that's it for this insert. Let's get back to the tutorial. So next I want to start Visual Studio up. So just go ahead and start this up and do create project, console app C++, and just console, we can call it simple message box. And I'm going to put it in our C:\asm source, src. And we can place the solution and the project in the same directory. And then we're going to click create, get rid of all the boilerplate. Going to get rid of that. Okay, so this is just going to be a very simple application, but it's going to make sense in the relevance of it will make sense. We're going to do something here in C, which is going to look very easy and simple in C so that we can relate to it in the assembly language version of this. So we're just going to call MessageBox, and we're going to call MessageBox with null, which is just the desktop. It's not going to be parented by any other window. And I am going to, in fact, let's call MessageBox A, which is the ANSI version. It's basically single byte characters. We're just going to do quotes without the L. There's no need for Unicode here. And we're going to say, just something like, hello world message box or something. I don't know. Anything's fine. And I'm going to call this MessageBox title from C++. And we will put MBOK here, which just will put an OK button on the dialog box. Okay, so now let's just run this by hitting F5. It'll run it in the debugger. And here's our message box, right? So pretty simple. It's displaying this. If I hit break here, so we'll hit break, and you can kind of see, here's the call stack. The call stack it's calling into MessageBox A. Tools, options, and just my code. Let's disable just my code. I think that'll open up the stack. And then if I go option, SYM for symbols, and then we go here, we can instruct Visual Studio to use the, Microsoft symbol servers. We can say, Oh, it wants to know what cache to use, and we'll just use the default cache it chooses there. I don't like to use the default cache there. I like to use the one that I create off the root or something, because these things which are in app data tend to get forgotten and lost, and then they might take up a lot of space and stuff. So I tend to like to put cache symbols and things, near the root. So it's loading all these symbols now from the Microsoft Symbol Server, similar to what we did with WinDbg. And you can see it added some more stacks. So we disabled just my code, and then we enabled access to the Microsoft Symbol Server. And then I chose to load all the symbols because we were in the middle of a debug session right now, and it had already tried to load symbols and couldn't, because we had, first of all, just my code was enabled. So it was, that when you have just my code enabled, you're telling it like, hey, I don't want to see other stuff outside my own code. And that includes some of these stacks and things with the debugger. And then of course, because it's not getting those, it's not processing those other areas of the stack, it's not going to load symbols for those. So we basically enabled seeing those other areas of the stack. And then we asked Visual Studio to reattempt loading all of those. It would have loaded those naturally had we been debugging and all this had been set up. So if I start this again, it'll have that already all set up. We won't have to do that. In fact, I can just do it now. So I'll hit stop debugging, and then we'll hit this, and then I can just hit the break here, and you'll see we'll get the same stack, but we don't have to disable just my code. We don't have to load symbols. It's loading all the symbols already. It's probably loading them from cache this time. You can see you get some call stack information. What's happening here? Here's our main function, right? And it's calling MessageBox A. So you can see MessageBox A is in user 32. Which is just a very standard, long-standing Windows DLL. And it contains, a number of different functions relating to, helper functions like this, like MessageBox and many other things. Anyway, we can see that it's now calling into NT user wait message. Now, NT functions, any functions that begin with NT like that means we've actually called into the kernel and something is going on in there, and we're waiting on something. We're waiting for some kind of response, or we're waiting for something to happen. And that's what's happening here right now as we're waiting. And what we're actually waiting for is the user to click OK on the dialog box. So if the user clicks OK, we'll actually come back to this function here. So let's actually hit the break. Okay, so we're here and we're in the kernel here. And what I'm going to do is put a breakpoint there on exit, and let's just run this again. And this is kind of basic stuff, but I just figured it's contextual, so I'll just give it you. Just kind of go over it really quickly. So I'll click OK, and when we click OK, right now it's pausing, probably because it's loading symbols. Yeah, so whenever you have the debugger set up to load symbols, especially if it's going to call out to get those symbols, you might see some delays when it hits a breakpoint, because it might be hitting a breakpoint and trying to load some other stack stuff up or trying to get some additional symbol information. Now that it's actually loaded whatever symbols it needed, let's run this again and see if it's a little bit faster. So we run this again, we have our message box. Let's actually follow the full steps here. So we did a break here, and we can see the call stack is in the kernel, and we're going to hit go. And now we're still waiting at this prompt. Now I'm going to click OK, and you can see it just jumps out and breaks right away. That's because it's already cached whatever it was looking for before. After I clicked OK, it was trying to load some symbols, basically, is what I'm saying. And this time it doesn't have to, because they're already cached. But you have to keep that in mind when you're debugging and you have symbol stuff set up and you're loading symbols remotely, like from the symbol server. That may cause little delays in your debugging experience or in the application or something. And you might think the application's locked up or stuck or something, but it may not be. So you might want to just check and see if it's loading symbols. In this case, you saw the little pop up and it showed that it was loading symbols. WinDbg does kind of a similar thing on the command line, and the little command window there, you'll see it says loading and stuff like that. Okay, so we have a very simple program here. I want to do one other thing now. I want to set a breakpoint before we call this function, and now I want to run it again. And what I want to do is I want to stop here before we call into the function, and I want to look at the disassembly. So we're going to look at the disassembly here, and what this is showing us is this is the line of code that's executing. It's calling MessageBox A right here. So we know the calling convention. This function, by the way, MessageBox A, takes 4 parameters, right? So we have 1, 2, 3, and then 4, right? So that would be RCX, RDX, R8, and R9. If we go back to the Ghidra discussion about calling convention, or if you go look at the documentation for the calling convention, either in the debugger tools or online at Microsoft, you can see that it's RCX, RDX, R8, and R9 for those first 4 parameters. Looking at that, we can see the parameter setup here. XOR R9, R9 is going to 0 R9. So it's zeroing the 4th parameter, right? So this is 1, 2, 3, 4. So MBOK must be 0. Well, actually, Visual Studio has some good symbol lookup stuff, so we could just hit like F12. And let me get out of this here and go here to source mode and hit F12. And it'll take me to the winuser.h file, which contains this define MBOK. And MBOK is what? It's the number 0. So that makes sense that we're zeroing out R9. Now, by the way, this is actually zeroing out the entire R9 register. R9D is the lower 32 bits, similar to the way that EAX is the lower 32 bits of RAX. So likewise, with the same thing we discussed with RAX, XOR R9D, R9D is really kind of just zeroing out all of R9. So that's our MBOK, basically. That's our MBOK. Then we see load effective address, and we discussed this actually in the Ghidra tutorial. R8 is the third parameter, and we can see that it's actually loading the address of this string. This is the actual title bar string, and we can actually see the prototype of the function. If we highlight MessageBox A, we go and hit F12, and it'll show us this, and this is the R8 parameter, which is the caption. That's the title bar of the window. We can see that in the disassembly window, it is actually loading the title into R8, which is pretty much putting a pointer to this string in the R8 register. So if I actually go and look at a memory window, and we can do that in Visual Studio by going Debugger, Windows, you go down to Memory, and then you just plug in the address there, this address here, which it says that it is loading into R8. We're going to hit Enter there. I need, in here, I need to put a 0x. So 0x just means it's a hex number, and Visual Studio does not know that that's what I mean, that that's a hex number, unless I put the 0x there. That's very common for some debuggers, and different debuggers behave differently. So depending on the context, you might need to put 0x to say, hey, this is hex. You might need to put something like in that case with the expression evaluator in WinDbg, you have to put 0n to indicate it's decimal and not hex, because by default, it assumes it's hex, right? So it's kind of the opposite of this. So we can see here's that address. This is the address, and you can see that the first character here is the M, and you can see all of these codes here are ASCII codes, and you can actually see the ASCII dump here. Of course, it is zero-terminated as well. That's a zero-terminated string to the title bar, and it's being loaded into R8. And if I go and load up registers, which we can do here in Visual Studio by going to Debug, Windows, and then registers should be here somewhere. There we go. You can see here are the registers. Okay, so here's R8. So R8 is going to get that address. Where's the address? The address is here. It's this address is going to end up in R8. Let me go. I have to step twice though. So we're going to clear R9. So does R9 have so R9 has a non-zero value. So watch the XOR zero that out. You can see that zeroes that out. And now I'm going to hit F10 again. I hit F10 before. Sorry, I don't have my little keyboard indicator thing on this demo, so forgive me for that, but I will say what the keystrokes are that I hit when they're important. I will hit F10 again, and now we're going to see R8 get loaded with this address here. Okay, so R8 gets this address, and again, just for clarity, we're going to go over to memory, plug this address in, prefix it with 0x to indicate it's hex, hit enter, and it's going to go to this address right here. That shows that this is the address being shown in the memory window. And then what we see here is a dump of the bytes that are at that memory location, and that is that string. So that's how that string gets passed, is it's being passed by passing a pointer to that string. By the way, this string, when the linker links this binary, that string becomes part of the binary, and it goes in this section where there's constants that are being held. Those constants are in the binary, and when the loader loads the binary into memory, it will load those constants and set them up so that when the program runs and it loads an address where it expects to find those constants, a particular constant, that constant will get loaded into the R8 register in this case, right? As shown in this case. RDX, okay, RDX is the second parameter, right? So we're talking C, D, 8, and 9. So D is the second parameter, and D happens to be the message that we want to display. So D being the message that we want to display, well, that's this message here, and the debugger is good enough to show us the message, but let's actually be good debugging tutorial kind of explorers here, and we're going to type in 0x and then plug in that hexadecimal number, and sure enough we look at the byte dump here and we can see that that is the message. So this pointer is going to get loaded into our RDX, and we're going to see that in the register window. So let me go to, we don't have to go to the debugger menu anymore, because now the tab will have the things that we open, the window that we opened. So I can go back to the register window by clicking registers, and we're going to look and see that RDX x64dx gets loaded up. Here we go. Boom. There it is, loaded with that address to the message. And then the last thing that happens here is ECX is zeroed. Well, ECX, is the lower 32 bits of RCX. So let's go find RCX. We can see that's got some non-zero value from some prior operation. It's not really important at this point. But what's going to happen is this code, this XOR ECX, ECX is going to zero out the lower 32 bits of RCX, which given the design of the processor is going to zero out really the entire register in this case. It's going to zero out the upper 32 bits as well. So we're going to see RCX change to 0, and that is the first parameter, which is the handle to the window. So the handle to the window of null is just represented by the number 0. And let's see what happens. And there we go, it's 0. So now all the parameters have been set up in RCX, RDX, R8, and R9. And now the function's going to be called. So we can see our breakpoint after the function returns will stop here after the function returns. So let's try to just hit F10 to step over the MessageBox function. Now in debugger terminology, when you step over a function, what you're saying to the debugger is, I'm not interested in what's going on in that function. I'm not going to trace into that function. I want to step over it. So I'm asking you, the debugger, to please run this function as fast as you can. I don't want to see the details of what's going on in that function. Just run it, come back to me, and when you come back to me, hit a breakpoint to stop right after at the exit point. So normally, if this function were a fast executing function, I wouldn't even really need this breakpoint. I could just hit F10, and once it would return, it would actually break right here at this XOR. So we can actually even try that. So I'm going to hit F10 right now. And notice when I hit F10, it doesn't just immediately go to the next step, because it can't, because that function call is being called. And step over a function doesn't make a function execute faster or do something different to come back quickly. When you step over a function which has some kind of UI prompt, what you're effectively going to do is you're going to be stuck waiting for the breakpoint until after that prompt is finished. So all we have to do is click OK here. And when we click OK, it will actually do the implicit breakpoint that it set for us upon return from that function, which it just did. And now it's returned. We can see that the return value from MessageBox is 1. And if we were to look up that function, in fact, we can actually just do that as an exercise. Here are the return values. ID OK. So 1 is ID OK. We can actually just pop that in here, hit F12, and there it is. It's 1. So after returning from this MessageBox function, which we just did here, you can see right after return, RAX is equal to ID OK. That just means we clicked OK. So whenever you do MB OK there, you're always going to get back ID OK, unless there's actually some system error that's unexpected, like highly unexpected. Pretty much all the time you're going to get ID OK back from that. Most of the time when people run MessageBox in a manner like this with MB OK, they're not really looking at the return value anyway. I was just pointing out that there is a return value here, even if we're not looking at it in the C code. I mean, we could look at it in the C code. It would be kind of silly in this case because it's always going to return ID OK. But I mean, you could actually do a check here and say, well, is it ID OK? But that would be silly here. There's other variations of the message box where you can enter in like yes or no. And for those, you might want to look at the return value because you want to see if the user clicked yes or if the user clicked no. That's a different thing. We're not doing that for this tutorial. Let's just, continue moving forward. Now we're going to go back over to assembly and we're going to do the same thing in assembly language. Okay, so I'm going to stop debugging here and we can just minimize that for now and go over to our source code. Whoops, sorry, where's our program? Here's our program. Okay, we're back here at the program, and what I'm going to do is pop in the changes. And what we see here are a bunch of different changes. Let's go through these. Okay, I'm going to start here at the top. Now we're going to go through this twice. Once as just sort of a brief overview, then I'm going to go back in more detail. Okay, so the first thing we're doing here is we are saying that we want to include user32.lib. That means we basically want to link to this library to find functions that we are using. Now let's go back over to the C++ program for a second and let's look at the project. Let's go over to the linker command line. So on the linker command line, you'll notice that there are a lot of libraries that are being linked here as part of the linking process. And one of them is user32. A lot of these are just standard Windows libraries. And so it's just linking with all of these libraries to see if they have functions that can fulfill needs of the application. So generally speaking, this is very generally speaking, When you build a C++ application and then you start to link it, you hand it off to the linker. And what the linker does is it looks at all the object modules and it goes to combine all these object modules into the final executable. And as part of that process, it also sees what symbols are outstanding in any given module, because many modules will use functions that are defined outside the module. Sometimes functions can be defined outside the module, but within the program, meaning in another module within the program. It's very common, though, to have functions that a module uses, like an OBJ, which is created from source code. So like you can compile a C or C++ program and create a .obj file, or you can assemble a .asm file and create a OBJ file. So you can create an OBJ file in both of these cases. The OBJ file is the object module, and the object module contains like these fundamentals, like the machine code that was generated from the compilation steps, and a bunch of interesting information that the linker can use to help understand, like, okay, well, what does this OBJ need from the operating system? So one of the things our program needs from the operating system is MessageBox A, that function MessageBox A. And in order for it to, it puts a little record inside of its object module that says, hey, I need this MessageBox A. And when the linker is processing that, it sees like, oh, this thing needs MessageBox A. So the linker is then going to go around and look at all the libraries it links to see which one has MessageBox A. When it encounters a library that has MessageBox A, it will determine, okay, we need this library for this program to run, and it will link the program to that library so that at runtime, the program will use that library to call the function it needs in order to perform whatever operation it would like to perform. So we can see that the regular C++ program is linking with all the default libraries, many of the default libraries for the operating system, or to support, linking to operating system libraries. One of them is very popular, long-standing library is user32, kernel 32 is long-standing, and so is GDI 32. So a lot of these have a history, and they're known to contain certain functions and whatnot. Some of that changes over time. Kind of out of scope for the demo, but just keep in mind that there's various libraries that the operating system comes shipped with. And very often when you create a program, you want to link to those libraries so that you can call them when your program gets loaded in memory, and you can make use of functionality that the operating system provides at runtime of your program. So we want to use the message box feature of Windows, and so therefore we want to link to the library that supports providing access to that function, that API. Even if the code to handle that API, if a lot of it is in the kernel, it doesn't really matter. There's still user mode libraries that we link to, and they do all the special stuff to call into the kernel to, perform whatever it is we're asking it to do. So in this case, MessageBox A is in user32, and so our application, whether it's written in C, as this example shows, or the assembly one, we need to be able to call into that. So if we go back over here, we can see that we're specifying that we need to link to this library. So that's just a hint there to the linker to make sure that it tries to link with this library in order to satisfy providing us this module, this ASM file here, providing support for some functions that we're going to call. And namely, we're going to be calling this function MessageBox A and from this module here. And so we want the linker to be able to find MessageBox A to tell us what to call. And by telling it what library we want to link to and putting something in here that this thing basically tells the assembler, hey, here's a function MessageBox A, and this function is not in this module. You're not going to find it here. It's defined outside of here. So just assume that it exists, and the linker will take care of the rest for us later. So basically the assembler will see this. It will create the right records and things to call MessageBox A. And what will happen is when the linker links this module with everything, it will go and try to find where MessageBox A is, and then it will fix things up so that this call ends up calling that library function MessageBox A. In a sense, we could say include live is basically telling the assembler, hey, make sure you put something within our OBJ file that tells the linker to go and link to this library in order to satisfy API calls that we're making, which are not defined within our own module. They're defined elsewhere. So in this case, they're defined in user32 live. This statement here, this extern_def, is a way of telling the assembler, hey, we have a function here that we're going to call, but it's not defined in this module. So it's not something that's going to exist. You're not going to know where to call. So basically be prepared to resolve that later. And the assembler is smart enough to set things up in a way where when the linker gets called, it will be able to resolve this function. Or if it can't, it'll tell us, hey, there's a function I can't resolve. Okay, I skipped over this const seg thing here. And this const seg here is basically starting a segment here. And it's basically saying everything from here to here is a const segment or const segment entries. And this is the name that we're calling the segment we're calling it const here. And this is kind of like a known possibility for this kind of segment here, this name const. And what we're going to do is we're going to put a couple constant strings in there. So we have two strings. One is hello world message and the other one is hello world title. So hello world message, db for defined byte. In an assembler listing, db is very commonly defined byte. And it's one or more bytes, and different assemblers might behave differently in how they let you define these, but it's very common in the MASM world where you can put like a quoted string and you can actually have a zero terminator there. So this is a zero terminated string and it's an ASCII string. And so this is the message that we want the message box to display. Here's hello world title. This is the same kind of thing. We have defined byte, and this basically means define one or more bytes. And what we're defining is 1 byte for each of these. So A is a byte, S is a byte, M is a byte, space is a byte, M is a byte, and so on and so forth, all the way to 0. 0 is a valid byte there. That's a zero terminator. So both of these are defining strings of bytes, which represent the strings in memory that we're going to pass to the MessageBox A function. Okay, .code defines the beginning of a code segment here. And it's saying, hey, put all this in the primary code segment. And what you can see here is there's a bunch of things going on, and I'm going to explain what these are. Okay, let's skip over this allocate shadow space for right now, and we'll come right back to that. Okay, so what we see are similar things that we just saw in the Visual Studio C program. What we see is that we're zeroing RCX. That's the first parameter. So that is a null handle, window handle. So we could actually add comments, and the way you add comments in a is you put like a semicolon, and usually you'll tab them out and they'll all be, uniform, and whatnot. Like we'll put them all out here. So we'll say like null hand wind to indicate a null window handle. And we can tab this one out to actually make this look nice and neat, because assembler listings are kind of nice when they're nice and neat. And we could even do this. We could say RCX equals that. And then we could actually go here and say RDX equals this. And I'm not going to put offset here. This just sort of means it is the offset. I mean, we can see it's offset here, but this is a comment. So it's just kind of saying like, hey, RDX equals, howdy world message. And if we wanted to, we could just literally copy this here. I normally probably wouldn't do that because it would just be redundant and they could get out of date if I change the message here. But for our example here, this is going to be clearer. So I'm going to actually say this equals the address of that. We can see R8 is loaded with the address of the title bar. And so that's R8 equals address of, and we can actually just copy and paste this here. And notice I'm being just sort of fast and loose and informal with the comments here. Like I'm not putting the zero terminator because we kind of already know that that's what's happening. This is just a comment to kind of just show, make it look easy there, for somebody who's maybe learning this or something. And then we have R9D is equal to 0. And this would be MBOK. So we'll just put MBOK there. And you can actually do some things like you could actually say things like MBOK, EQU, and then 0. And then you could actually say move R9D, MBOK. But I'm not going to do that right now. I'm just going to leave it the way that, we know that this zeroes it out. And we actually know that MBOK is 0. So let's just stick with that for right now. In fact, I can just put 0 like that, just if it's easier. All right, so zeroing EAX, I'm going to actually do that down here before we return. So we will return and I'm going to zero the, just to say that everything is successful. So we set up the parameters, right? Parameter 1, 2, 3, and 4. And then we call MessageBox A. That will sit here. So we can actually say display MessageBox, wait for user to click OK. And then we do this cleanup of add SP28. I'm going to explain what this is. And then we zero out the exit code. So we can just say exit code is 0 success, and then it'll return, and that 0 will get returned to the command line, as we saw before when we, passed one, when we returned 1, 2, 3 in our EAX. So now let's go back and examine this and its counterpart, which is this. So basically, this is subtracting 28 hex from the stack pointer, and this is reversing the effects of that before returning by adding 28 hex back to the stack pointer. So if we go to calc here and we plug in 28, you can see that's 40. When the function gets called, okay, its stack pointer points to the return address of the caller. In this particular context, when we get called, the stack is going to be misaligned. It's going to not be on a 16-byte boundary. It's instead going to be on an 8-byte boundary, or in the middle of a 16-byte boundary, not on a 16-byte boundary, instead in the middle of a 16-byte boundary, which is misaligned. Okay, by design. That's because, in a sense, this is considered the prologue code for this function, and it is up to the prologue code here to realign the stack. So it's going to include this extra 8 bytes here. Now I say extra 8 bytes because I haven't explained what the other 20 bytes are, right? Or 32 bytes, I should say, right? So what I mean by that is what we have here is we have 28 hex, which is 40 bytes, right? And we have 8, which is 8 bytes, and this is for prologue realignment, stack realignment to 16-byte boundary. Now just bear with me if you're not following this, okay? And then we have unaccounted. We've already accounted for this 8. This 8 is 8 bytes right there. What we haven't accounted for here, though, are there's 28 bytes, which is 32 bytes, okay? And you'll notice that if you divide that by 8, it comes out to 4. And this is a shadow space for the 4 registers used to pass the first 4 parameters. But really, it's up to the callee, that's the function being called, to use this space however it wishes. By design, though, the calling specification requires these to be here. Now, I'm going to point out a place on the documentation where you can read more about this if you want to. If it sounds complex, don't worry. Just let it go into your system. This kind of stuff is always going to sound a little weird and strange at first. You need to see a few different examples. You need to read the docs a few times, trace through some code yourself. That's always very important. If you're ever in a discussion where somebody's springing stuff on you and it's like they're like, you don't get it yet, or something, that's loony. Okay, so just go easy if you haven't seen this before. And once you get into it, it's really not rocket science. It's not complex. You just need to, it's like an intricate puzzle, and you just need to have your own solitude time of digging into it, absorbing it, and you'll get it if you want to. And if you don't want to, you don't have to either, right? Like it's the kind of thing that if you're interested in it, though, don't think it's some kind of high science or something. It's not. So you can read about this here. So here is this is the Microsoft site here, and it's talking about the x64 calling convention. So you want to read about shadow space or shadow store, and you can search around and read a little bit about it. People have written about it and whatnot. This is the part right here that says the stack pointer must remain 16-byte aligned in any code which isn't really part of the prologue or epilogue. And I would just add to that in the case we're looking at, by design, when the function receives the stack, meaning when it gets called on its first little instruction there, by design, the stack is going to be misaligned because it was aligned before the caller called the function we're talking about. So let's go back over here. You have the kernel, right, calling main below. Right, so the kernel is going to call this main below. Right when this gets hit right here, when this function, when this lands on, if we put a breakpoint here, or right when this instruction, before this instruction executes, okay, by design, RSP is going to point to the return address. Let me actually separate all this stuff out here because it makes it look like that's part of it. So let me actually connect this here. So kernel calls the main function below. So the kernel calls main. When the kernel calls main, RSP points to the return address of the caller. So the way you can look at it is there's kernel code here, kernel is executing, right? And the stack is, let's say, 16-byte aligned here, right? And it goes and calls main. When it calls main, implicitly the processor will push the return address of the kernel instruction, the one that follows the call. And I can actually show you that in the debugger and stuff. We'll look at this in the debugger. The kernel calls main, and at the time it calls main, the stack is on a 16-byte alignment. And I'm going to show you in the debugger how you can check the alignment, what this 16-byte alignment means, and how you can identify it and look at it. So just, if you're lost, great, thumbs up, that's good. Just, get used to being lost. It's kind of like the Geeter stuff, that should just be something that's just kind of like you handle it so well, because it'll just be, there's going to be so much complexity in this world with technology and stuff like that. So, just like I said, slough it off like that. It's the way to be, right? I think personally, okay. Your mind will be able to handle more data and more information and more complexity and whatnot, as opposed to, feeling like you have to retain every little single piece of detail. So basically, when the kernel hands off to main, at the time before the call, the stack is on a 16-byte alignment. But because the return address back to the kernel, the instruction that follows the call, gets pushed onto the stack by the processor, and that address is 8 bytes, it misaligns the stack in terms of being 16-byte aligned. So the stack then becomes like 8-byte aligned, or it's aligned in the middle of a 16-byte boundary, which is not 16-byte aligned. And the callee, in this case, that's the destination of the call. So the callee is main. The callee expects that misalignment, and its prologue code, the code that executes before entering the main portion of the function, its job is to realign that stack back to 16 bytes, or at least ensure before it hands off to any other function that it is aligned before that call takes place. And then the same thing repeats. If another function gets called, its prologue code will adjust the stack to fix the natural misalignment caused by the push of the return address of the caller on the stack. So we're going to go into this in detail. So let me actually just get rid of this for a second. So if we go back here, this will explain the shadow space. RCX, RDX, R8, and R9 are all used to pass those first 4 parameters. So this shadow store area is meant for use by the callee to save those registers there. And historically, it's meant to ease the debugging experience. I wouldn't always assume that everything will be that way. You have to look at the particular context and how something is built. If it's release build, basically look at this as scratch space that's allocated by the caller that the callee can use as it wishes. And it has an initial purpose, historically speaking, but it can be used for other purposes. And there's discussion about that online, and you can read about it. But the point I'm trying to make is that as a function that's going to call another function, which is what our little program does. It's going to call another function. It has to assure that the stack is aligned properly and that it allocates this space on the stack before calling this other function, because this function that it's calling is going to expect that this space is available for it to use to store registers there as needed. So there's 2 things that callee is going to expect. One, it's going to expect that it's going to be misaligned by 8 bytes that it will fix in its prologue. And it's also going to expect that 32 bytes have been set aside just after the return address on the stack that it can use as it wishes. What this means is we have 28 bytes total, I said, which is 40 bytes, right? 28 hex. And 8 bytes is for realigning the stack, which we're going to go over in more detail in the debugger. Then we have 20 bytes. And really, this is shadow space that's meant to hold up to 4 registers. Really, it's if the callee wants to, it can store RCX there, RCX, RDX, R8, and R9, or it can use that space as it wishes. So it's up to the callee to use it as it wishes, but it's up to the caller to ensure that space exists there. If the caller does not ensure that space exists there, and the callee uses that space, it will end up corrupting the stack. So in a sense, you could loosely think of, 8 of the bytes is for callee to optionally store, save RCX for debugging purposes. So if you want to see what the registers were set at the time of the call, you'll be able to examine them in these memory locations so long as the callee used them for that purpose. So you have to make sure that the callee is using them for that purpose. You don't want to assume that. So this accounts for the other 32 bytes, right? So we have a total of 40 bytes here that are being added to the stack by our quote-unquote prologue code. And 8 of those bytes is for stack realignment, so that the stack after our prologue is aligned on a 16-byte boundary, and so that we allocate the space for up to 4 registers, or 32 bytes, that the callee can use as it wishes, if at all. It may not use it at all if it doesn't want to. And so that's what this statement does. This statement basically will take a stack which is misaligned, which is aligned in the middle of the 16-byte boundary, and the 8 there on the 28 will realign that to a 16-byte boundary. And then you have 32 bytes, which is 2 sets of 16. So that keeps it aligned. That doesn't misalign it. And that extra space is meant for scratch space as the callee wants to use it. And so we're including that there in case the callee uses it. After we do that, now if we didn't do this, we might see a crash or some kind of malfunction when we call this function here. And in fact, I can actually show you some. We'll actually remove these and we can test it out. This is actually just reversing the effects of that. So we're done with the call. We're about to return to the caller. So what our epilogue code is going to do here is just restore the stack to where it was. And right now, after it does this add RSP28, what happens is RSP now once again points to the return address of the caller. And we'll go through this in some detail in the debugger so you can kind of see the caller's return address and all this kind of stuff, right? So let's actually build this function and let's actually see what happens, okay? So the first thing we can do here, so let's go back over here and get our build line here and let's build this. Okay, that's great. We got our build line. Whoa, hey, where's our debugger line? Okay, so here's our debugger line. We're going to go into the debugger now and we're going to run this. So let's just hit enter on that. And here we are in the debugger. And what we're going to do is just hit a breakpoint here for starters, right there on main proc. And I'm going to hit just G. And there we go. We're at the first statement. Now, the first thing I want you to see, and we're going to go through this twice or 3 times or something like that, because I want you to see something. Okay, notice that upon entry, so we're at the entry, none of our functions code has executed yet. Notice that RSP, look at RSP here. So this is the value of RSP. In fact, let me just show you how I would do this. I typed in R like that, but what you can do is say RSP, and that'll show you the stack pointer, or you can say just RSP, and that shows you the stack pointer. Another thing you can do is you can use the evaluation question mark feature I told you about, but then you can put an @ sign with RSP, and that represents the RSP value within this evaluation function. So when you do that, you'll get the same value back, but it will be within this evaluator. You can like actually use the value, and you can say something like +8, for example. So if I add 8 to the stack pointer, you can see it goes from 38 on the lower byte here to 40, which is what would happen. If you add 8 to 38, you're going to get 40 hex. Remember, this is hexadecimal. So what I want to show you, though, is when we get RSP, okay, when we get RSP, we get it misaligned. Now, how do I know it's misaligned? Well, I can tell you right away. I see something here which is not 0. If I look at the last thing, and I call that a nibble, and I think I got that from like an Apple disassembly listing or something. I got that from, I think Apple used to use nibble as a half of a byte. So a whole byte. So for example, a whole byte, like if I wanted to say 255 in decimal, 255 in decimal is FF. So that's 2 hex digits FF, right? So that's F, and that equals 255 in decimal. And that's because if you think about it like base 2 counting system, like for binary, hexadecimal, you can go look it up and look at tutorials on it, but hexadecimal is just simply base 16, right? So digits are just symbols anyway, right? Like the number 1, the way it's written, in any given language doesn't really have significance in and of itself. It's just a symbol, and you look at it, and since you understand the language, you understand the value that it has. So when you're counting 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you go to 10 and you say 10, 11, 12, 13, 14, all the way to 19, and then you say 19, and then the next one would be 20. That makes perfect sense to you, right? If I say to you 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, You start going, what are you talking about, A, B, C, D, E, F? Like, that's not counting or whatever. Well, why not, right? So like, that's the way you got to look at it, right? Like, in other words, why is 0 through 9 and then wrapping around and carrying over to the tens place with 1, 0, and then 1, 1, 1, 2, as I just counted, right? Why is that normal, but counting from 0 to F and then rolling over after I exceed F and I go to, well, after F in hexadecimal, it goes to 10. So like hexadecimal, I'm just going to open up another text thing, and let me just expand this a little bit, make this a little bigger. So here's normal digits, right? So, I mean, this is really not complex. It's just a matter of being around it a whole lot, right? So don't even worry, like if you're thinking like, oh, what is this? Da, da, da. Okay, so here's normal counting, right? Now you could come up with your own symbols, right? You don't need to use these symbols to even count in this system in base 10. This is base 10, right? So you don't need you don't need to use these symbols. We just know them very well. They happen to make sense to us, right? What's really important with base 10 is that you have 10 things that can be represented here. And then once you exceed or reach that last one, you have nowhere else to go because you've run out of symbols, right? There's nothing after 9 in base 10, right? There's nothing, you can't count to, triangle, right? Because that doesn't exist in base 10 counting in the way that we know it. So what we do is we put a 1 in the ones place, and then we carry that 10, because we've reached 10, we call it base 10, so we carry over to the next place and we put a 1 there, right? So base 16, that's what hexadecimal is. Base 16 is kind of the same thing as decimal, right? You count all the way to 9. It's pretty much the same thing when you get to 9. Now you get to 10. Instead of carrying over when you reach to 10, you can actually put 10 in a single, you can put 10 in a single digits place. This is 10. That's 11, that's 12, that's 13, that's 14, that's 15. So just the same way in base 10, you can reach up to 9, but you can't put 10 in a single digits place in base 10. Like when you get to 10, you're really in 2 digits places, right? So the single digit, each place represents up to 1 less than the base, right? So for base 10, you can go from 0 to 9. Base 2, you can go 0 to 1. It's 1 less than the place. And then you carry over. So like binary, if I'm going to count to 4 in binary, that's going to be, that's going to be like 1 and then, that's going to be 0 and then 1. Right? And then you're not even beginning, you can't fit 2 in the single place. You have to carry over already. So this is 0, this is 1, this is 2. And now here's 3. Now, if you want to go to 4, you actually have to carry twice, right? You have to go 1, 0, 0. That's 4 in base 2, right? That's binary. And that has advantages because electrical 0 and 1 can represent 1, 0 and 1. So that's why we use binary there, right? So there's probably plenty of videos. I think there's certainly plenty of videos on all this stuff, right? So base 16, which is hexadecimal, is just, is each place can count from 0 to 15, right? Because it's base 16. So what's 1 less than the base? 1 less than 16? 15. So that's 0 to 15. You can fit 16 items in a single place. 0 through F. That's 16 different values in the single place. Once you exceed this place, right, and you want to count higher than 15, if you want to count to 16, well, that's going to be 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. Now, you're probably thinking that's 19. No, that's 19 hex. You got to say hex, because if you say 19, everybody thinks you mean decimal, which is not really true, right? You should say 19 decimal, but we don't go around doing that. We assume 19 means 19 decimal. Unless you say hexadecimal, or context might, determine what it means, right? Like if you're talking with certain people and you're all talking hex, you just say 19. So what is 19? Well, the way to look at that is you've got 1 in the 16s place, right? So that's 16. And then you add 9 to 16, right? So that's going to give you 25, right? So we can actually look at that in the hex calculator. If you go to the hex calculator, you've got 19 here, right? So 19 gives you 25 in decimal, right? So really, this is 25 in decimal, right? So if you want to translate that, it's 25 in decimal. So what happens is you can go in decimal. So I should actually be saying D for decimal or something like that, right? So we can differentiate. If you get as high as 1F, again, we can't have more than F in a single place, right? We just can't do that. So we have to carry over, and the way we carry over is we go to 2O. So this means we have 2 16s and no ones. The ones place has nothing in it, right? It just went from having 15 in the ones place, and we can't put anything else there, so we carried over to the 16s place. You know, I mean, in a sense, like if you think about decimal, right? You have the ones place, you know, the tens place, right, and so forth, right? Well, base 16, you have the ones, you know, place, right, in a sense, and the 16s place, right? So every count here is equal to 16 in base 16. Whereas in decimal, if you know, so if in hex, if I were to say 20, right, like that's actually going to be 32 in decimal. If I were to say 20 in decimal, right, 20 in decimal is like 2 times 10. It's 2 in the tens place plus 0 in the ones place. Whereas 20 hex is like saying 2 in the 16s place plus 0 in the ones place, right? So these number systems are really about what does each place mean in value. And usually you only put something in that place if something can't fit in the lower places, right? And you roll over or carry over, you know, if you're adding, for example. So that's a really quick hexadecimal overview. Let's actually close this and get back to the debugger here, because what I want to show you is that 16 is kind of interesting, right? So if I say 0n16, which is decimal in this little debugger evaluator, you can see it shows me that 16 is 10, and that makes sense. The reason why it makes sense is because 16 is one amount of 16, and we can't fit 16 in the ones place in hexadecimal. It only goes 0 to 15, so you have to roll over to that. So every 16 bytes is actually going to put a 1 in that second hexadecimal digit. Now, another interesting factoid actually regarding hex that is probably helpful is that a hexadecimal digit can be represented by, you know, and I'm not going to draw this all out. So if this were binary, so this would be like hex, and this would be binary. Let's just go here and say like ... And let's just put half F here for 15. So 15 in binary is all ones right there. So it just so happens that each hex digit represents 4 binary bits. And that becomes an easy thing for developers to identify and kind of think about. And you can kind of translate, like if I think about F, if somebody says to me, you know, that's F and hex, you know, right away I know that there's all ones in that particular hex digit place. So if you have something like FF, you know right away that's 4 binary ones and 4 binary ones, which is basically 255. You know, that's a byte basically also as well too. 2 hex digits is a byte. A byte is 8 bits, right? And this is the decimal value. I should put decimal to clarify. So it becomes very convenient, you know, like if you're looking in the debugger, right? So if we go to the debugger, where's my debugger? Hello, debugger. So if we look in the debugger, what we know then is if you're 16 byte aligned, you're going to have a 0 in the last place. If I put 8 here, which is not 16 byte aligned, that's going to have an 8 in the last place, a non-zero value. In fact, anything that's not that has a non-zero value in the last place here is not 16 byte aligned. So if we go back to the stack pointer, we can see that the stack pointer before any of our function executes has an 8. And that 8 is actually the size of a register. It's also the size of an address. And it actually is because the stack pointer was increased by 8 by the processor, because the processor put the return address for the caller to us on the stack as part of the call instruction that was performed by the caller. Now we're going to go through this. We're going to actually do this again from the perspective of the kernel that is calling into main here. So you'll be able to see like the whole thing kind of unfold, and we're going to look at it in the debugger as we go through it. And this is a great way to learn. So if you're ever really wondering how all this stuff kind of works, you almost don't even need a tutorial. If you just have a debugger and you have some code that you can write in like Visual Studio or some assembler or something, you can toy around with this and examine it in the debugger. And tutorials are good. And you can also, though, maybe have questions from what you see there, and you might be able to search around and find some answers and kind of be resourceful like that. The stack pointer here, as you can see, is not 16 byte aligned. Otherwise, it would have a 0 there. So what we do in this prologue code of ours that we added, this sub RSP28, and by the way, we're doing a sub, so this might be a good chance for us to talk about the stack for a second. Okay, so let's just start with a simple example here. The stack pointer doesn't really start at 100, right? But we're just going to do that so you can kind of see, sort of what happens. So the next thing is that, let's say the kernel calls main, right? When the kernel calls main, the processor is going to subtract from the stack pointer. It's going to subtract 8 bytes from the stack pointer, and then it's going to store the kernel's return address there. The processor does that. The main function of ours will inherit this stack. And then let's say the main function does what we see. It does that sub RSP, 28. Okay. And when it does that, well, F8 minus 28, well, we can actually just do the subtraction here. We'll just go and say F8. Okay. So, sorry, we'll say F8 and then we'll subtract F8, subtract 28. Right? And you can see that that ends up being D0, right? Now, it's actually easy. I didn't actually go to the calculator, right? So 28. So the way to do this is you see that, well, 8 minus 8 is going to be 0, right? So that's the 28 here. Let me just put it here. So we have F8, and then we have 0, 28, and 8 minus 8 is 0, and F minus 2, well, that's E and D. So that would be D0. Right, so the stack goes to D0, and that's what we saw in the calculator there, right? Now, 16-byte aligned by the main function. So by the main function prolog sub RSP, 28, which we already have over here. But the thing that's interesting about this is you can kind of easily see, like when you look at hexadecimal, you can kind of see, like when you see an 8 here, 8 is the size of a register. It's also half the size of 16-byte alignment, right? 16-byte alignment is, if I take a value like, D0 and I add 16 to it, you can see that that's going to equal E0. That's still 16-byte aligned. If I add 8, it's going to equal D8, which is not 16-byte aligned. So you can look at hexadecimal numbers and kind of easily identify if something is 16-byte aligned. So you can see when the kernel called main, the kernel gave us a stack that was not aligned on a 16-byte boundary, not because it had that stack, but because the processor pushed its return address on the stack, which a return address is 8 bytes. And so that basically decreased the stack size by only 8 bytes, which means now the stack is not 16-byte aligned. It's aligned between 16 bytes, like in the middle of 16 bytes, right? And so us as the prolog, us as the callee, the one receiving the kernel's call, one of the first things our prolog will do will fix the stack to adjust it so it's on a 16-byte boundary. That's what the 8 does. So if I just did this, it would fix the stack alignment. And technically, we could do it that way. We could do sub RSP, 8, and then have another instruction that does sub RSP 20. That sub RSP 20, okay, and in fact, maybe that would have been a better way to present this. So for example, I could have easily broken this out and just said like this and put different comments, realign stack to 16-byte boundary. This is part of the agreement between callee and caller. Prolog will fix the stack up to be on a 16-byte boundary. And then what we're going to do is we're allocating shadow space. That the 20 is really the shadow space, not the 8 is not really part of the shadow space, even though the comment said that. But here's the thing. The reason why I had it the way it is you're very often going to look at code in assembly language and you're going to see like subtraction from the stack, and you're going to see things like whether, there's an 8 here or not. And you just might have to track stack positioning and whether it's aligned or not in certain contexts. And it's just a good thing to be aware of as you start to look at these disassembly listings, as you start to use a debugger to maybe peer into things. It can help you to learn about these things by, looking at those nuances and kind of understanding them. And it becomes second nature. Like you look at a hexadecimal value and you see like, oh, well, that ends in a non-zero hexadecimal value, so it's not 16-byte aligned. And you know that because hexadecimal is base 16. And so that 16-byte alignment means that, the last digit must be 0, because anything in that last digit means that it's not aligned on a 16-byte boundary. All right, so we want to be aligned on a 16-byte boundary before we make a call to another function, because when we make a call to another function, it's kind of like when the kernel called us. We have a 16-byte aligned stack. We call another function. The processor pushes our return address on the stack, and that callee function, the function we're calling, it receives, it gets execution or control with the processor. It starts running with a stack that's misaligned by 8 bytes because the processor pushed our return address on the stack. So we had an aligned stack, we called a function, the call to the function pushes our return address on the stack, which misaligns the stack. When the callee gets control, it has a stack which is off by 8 bytes in terms of 16-byte alignment. It adjusts the stack by doing a sub or pushes or whatnot in order to get the stack 16-byte aligned, or whatever alignment it happens to need. But most of the time you'll see it's going to, enter the function, and the prolog will align it on a 16-byte boundary. And if you look in the documentation here, you can read that the stack pointer must remain on a 16-byte aligned, 16-byte aligned in any region which is not the prologue or epilogue. So it's kind of talking about that. The stack, this one has it as well too. So you can read these, articles if you want to. What I'm doing in one sub function here is I'm allocating space on the stack. I'm allocating 40 bytes on the stack in a sense. 8 of the bytes is to achieve realignment on a 16-byte boundary, and the other 32 bytes is to create that shadow space. And so in a sense, we get called by the kernel, and the first thing that we do in our function is we subtract from RSP 28. And what that does is it makes the stack pointer go to D0. Now, the way to think about that is let's say this is a memory address, right? So 0D0, RSP points here, right? And so you might say that this is shadow, shadow 8 bytes number 1, okay? And let me just put 4 of these here, right? So then we go 8 bytes up in memory, and that's for number 2. Let's put number 3 and number 4. And so here's another thing too. If you're adding by 8 bytes, so I add 8 to D0 and I get D8. I add 8 to D8 and I get E0. It's very easy to add 8 bytes when you're, working with hexadecimal. So I add 8 to D8 and I get E0, and I add 8 to E0 and I get E8. So it just keeps increasing by 8. It goes from 8 to 0 to 8 to 0, and the 16th place just increments as you go up. So you can see that we are at D0, we add 8, we're at D8, we add 8, we're at E0, we're at E, we're at E0, so we add 8 and we're at E8. So these are the locations. D0 is shadow 8, 8 shadow bytes number 1. D8 is 8 shadow bytes number 2. And there's 32 of these shadow bytes, right? You might say that EF0 is, you could call this scratch 8 bytes for 16-byte realignment, right? So this fixes up the alignment. So by we got it when it was at F8, but by adding 8 bytes or subtracting 8 bytes from that, we realign it. So F0 is 16-byte aligned. So now it's 16-byte aligned, and then the 32 bytes of shadow space actually is 2 16s. So allocating the shadow space by subtracting an additional 32 bytes, basically that just keeps things 16-byte aligned, but it adds the shadow space. Now we can call any APIs. When we call an API, its return address is going to go here at C8, our return address. So main's return address will go here. So when main calls API, main's return address pushed onto stack here by the processor. Processor as part of the call, right? So there we go. What will happen is when we call that API, it's going to have prolog code that's going to fix the alignment of this. So this becomes 16-byte aligned. All right. So and so on, right? So the callee gets a stack. It knows it needs to include at least an extra 8 bytes on there to fix up the alignment. So it's on a 16 byte, boundary, the stack is, when it's past the prolog code. And then before we call any other API, we want to make sure that we have shadow space on there. In this case, our prolog code is calling in, we're going to call one API. So in one fell swoop, I subtract 28 from the stack pointer, which essentially allocates the shadow space and it realigns the stack to a 16-byte boundary in one fell swoop. And then we can call that API. So we can go over here. We can go back. Let's go back over here and let's actually just see what happens here. So if we look at RSP, we can see that it's misaligned, right? Because we see an 8 here. And you can also see that up here. There should be an RSP. So here's RSP. You can see the 38. That 8 right there at the end, that means misalignment in terms of 16-byte alignment. It doesn't meet the spec that is required for the calling convention here. So after we get past our prolog code, we want this to be 16-byte aligned. So let's hit the T command to trace one instruction, which is going to do that subtraction of 28. And because we see a subtraction of hex 28, well, we know that if you subtract 16 from something that's misaligned, so if I take 38, let me go to the calculator to show you this. If I take 38 and I subtract 16 from that in hex, which is 20, okay, and I hit enter, we have 18. So we still have something that's not aligned on a 16-byte boundary, right? Because if you subtract 16 from something that's misaligned from a 16-byte boundary, the result is going to be something that's still misaligned because you're subtracting in multiples of 16, and those aren't going to help you realign something that's misaligned from a 16-byte boundary. You need something that's at an offset. In this case, because we're in the middle, we want to fix that. So you need an 8 in there in order to kick that to the right alignment. So if I go back to that example, the example we have here has a stack pointer that ends in 38. So let's just put that 38 here. If I have that 38 here and I subtract 8, I'm going to be aligned on a 16-byte boundary. Look at that. I turn my 38 into a 30. If I take this 38 and I subtract 18, right? That's 16 plus 8. Well, that's going to align things, and it's going to subtract an additional 16. See, and it does. You can see there's 20 there. And as long as there's 0 in that first hexadecimal digit, you're 16-byte aligned. Okay, so let's try one last one here. If I take 28, that's the one that we're going to be doing. Boom, it gives you 10. And you're 16-byte aligned, and we also added an extra 20 on that, right? So, or we subtracted 20, which allocates an extra 20 bytes of space, or 32 20 hexadecimal bytes, which is 32 bytes decimal. All right, so here's the stack pointer. Here's the instruction we're on, 28. And basically, this is going to subtract from RSP the value of 28. This RSP ends in an 8. This value that we're subtracting ends in an 8. That means it's going to fix the alignment, and that's what the 8 does in this subtraction value here. And then the other 20, which is left over, that's our shadow space. So by looking at that subtraction there, I can identify two things. I can identify 8 bytes for realignment to a 16-byte boundary, and I can identify that there's 32 bytes there, 20. That is unaccounted for, right? We know what the 8 bytes does, but there's 28. And the 20 there is 32 bytes. And that's our shadow space. So you'll get used to seeing something like that, and you'll see like, oh, well, there's an 8 there, so that's fixing alignment. What's this extra 20? Oh, shadow space, or something like that. In other functions, you might see it subtracting to make space for other variables and structures and things like that, as we did with the Ghidra tutorial. And so you'll be, like looking at these things will help you kind of understand like certain hexadecimal values and their relationship to what's going on with the stack and where things are located and things like that. So let's actually hit trace now finally, right? I'm talking so much. We're going to hit trace, and what happens to our stack? Well, look what happens to our RSP. Our RSP is now ending with 810. Okay, so before our RSP, if we look at it here, here's our RSP. It had 838. So it has gone from 838, so let's actually look, to 810. And if we just bring this over to our scratch pad, let's just bring this over here. So there's where it was. And this is where it is now. Okay, so all this stuff here is like a wash. We don't need to worry about it, right? Like it just doesn't matter for our sake of our discussion, because those values just cancel each other out. So the stack pointer was here, right? And then after our subtraction, the stack pointer went to here, right? What this means is that, here at 30, this is 8 bytes. This is 8 bytes for realign on 16 byte boundary. And then we have these shadow bytes, which I'm going to actually just copy this here, and I'm going to change this to be, this would be 28 and 20 and 18 and 10, which is what we have here. This is the 10 right here, and I can actually just put that here and put that there, and maybe, I don't know, maybe tab this out or something, just. This is a little ad hoc here. I didn't really expect to go down all this, but in the moment here, it it sort of made me feel like, oh, you know what? This is maybe relevant to, being able to interpret things from Ghidra and kind of doing all that. So I like to go with things like that. So hopefully you don't mind. So what you can see is that our Prolog code basically fixed the stack, so it's now aligned on a 16-byte boundary as part of the agreement we have between caller and callee. And then we have allocated the 32 bytes that are required for us to do before we call something else. So now that we have done all that, we can go to our debugger. So where's our debugger? Now the remaining things in our debugger are simply to set up for the next call and make the call. So it's simply going to go down. We can actually go through this pretty quickly. So I'm going to hit the T key. Now I want to show you something here. If I hit the T key, it's going to zero out RCX. So you can look up here and you can see RCX has a non-zero value. I hit T and it zeroes it out. Now I want to show you something. In WinDbg, when I hit the T key, if I want to execute the last command, which is the T, all I have to do is hit enter. So the next one is going to load the message, howdy world message. It's going to load that address into RDX. So if we look at RDX, we can see the value, which is in RDX, and it's going to change. And I'm just going to hit enter. And it goes to the next statement. And what we can actually do is verify this. We can use DA, which is dump ASCII, and I can say the RDX register. So if I dump ASCII, and it'll show us what's at that address. Another way we could do that is I could say RDX, and I could get the address. And with this physical address, I could say dump ASCII, and I could just use that address directly, and it would produce the same thing. And there's reasons why you'd want to use one or the other in different contexts. There's a lot of things you can do with the debugging tools. You can automate stuff and create little macro things and everything like that. So some of that stuff comes into play, in terms of accessing registers and things like that, when you can do some of these more advanced things. But it's also great for interactive work too as well. And so the next one is going to do the same thing, but for the title, the caption message, and that's going to be loaded into R8. So if we look at R8, R8 has this value, and you're going to see that change. And I'm going to hit the T. I'm going to type T and enter. Since I entered other commands, I can't just hit enter because the last command that ran was not the T command. So I have to enter T. And when you enter T, you'll see it updated R8. And we can actually just verify that with DA for dump ASCII add R8, right? It's R8? Yeah. Okay, R8. And there it is. Now, you can also do DB for dump bytes. Okay, dump bytes. And I can actually specify the address here. And this command is documented. So D, you can look at the D command. There's D, DA, DU, DB. It's all kinds of ways you can dump memory. These are commands that dump memory. So basically this DA command dumped the memory as an ASCII string that's zero-terminated. And this DB R8 dumped memory as a string of bytes with putting texture. This is a very standard, this goes back, to like debug.com and DOS days. I'm pretty sure, I know CPM also had something like this as well. So it goes kind of way back, DB. And so it's just different ways of looking at memory. But what we know is that the R8 register has an address that points to memory that has this contents. And we also know that the RDX points to an address in memory that has the contents that we showed before. And that's how our function is going to tell the MessageBox function which strings to use when it displays a message box. We are basically supplying the addresses to these strings to the MessageBox API. And we're doing so in registers that it knows how to interpret. So by using the RDX register and using the R8 register for those two strings, the MessageBox API is totally prepared to, consider and look at those registers to have the values that, it would expect for the message itself as well as the title bar. So this is all about following the protocol, the API, that kind of thing. In C and C++, you kind of usually don't have to worry so much about these particulars because you have nice, neat functions which call other functions. But in this case, we're actually crafting the calls ourselves. So we have to be aware of what the calling conventions are. Usually the compiler takes care of all that. So the next one is going to zero out R9, and that's for MBOK. So R9's already zeroed out, so we're not going to really see any change there, but we'll just run that anyway. And then the next call is to go into MessageBox. Now I'm going to do the P command to jump over the MessageBox function and break after the return. So we could do that two ways. One is I could set a breakpoint after, and I think I'm going to do that this time. I mean, I could do the P command, but that's just a little bit more obscure. I want to make it kind of simple and just set a concrete breakpoint there. And then I want to use the G command to go. So I'm going to do G. And there's our message box. Okay, great. So the message box is here. So we're going to click OK, and it comes back to us. It returns to us, and we can see RAX has the 1 for MBOK. So what we do now is we're going to restore the stack by adding our 28 to RSP. So to show it over here, we found the stack right at this position. So by adding 28 to 10, 28 to 10 will bring us back up to here. And this is actually the return address to the kernel. If I go here, well, actually, let's go RSP. We can see that it's at the 810 value, the stack is, and it's aligned. And now we're in the epilogue code, technically. This is like the cleanup epilogue exit code. We're going to trace one instruction to do this add RSP, 28. And we will look at the RSP value, and you can see it's now back to that value that ends at 38. So it's back to that, what I'll call natural misalignment, that when we do this ret instruction coming up, so we're zeroing EAX here to say that everything was successful. So that's our return code. So if you look at EAX RAX is 1. So if I do a T, it's going to zero that out. And this ret instruction, so let's actually look at RSP. So you can see RSP has not changed since we did that subtraction. That's expected because there's been no stack operations. And what we can do is I'd like to do a DQ, and I'd like to do an RSP and an L1. Well, let's just say DQ RSP. So if I do DQ RSP, you can see that it dumps a bunch. DQ is quad word, dump quad word. Quad word is 8-byte word, which is 8 bytes. So this is the current thing that the stack points to. And actually, I think there is a column thing where you can say -C1, I believe, for one column. Yeah, so this kind of gives a better representation of the stack in a sense, although this is actually getting higher as it goes down. So the stack here is kind of going to, it's going to be popped off and go downward. So the next thing to pop off the stack is going to be this address here, and this is the kernel address. Now there's another dump function. You can actually do DPS RSP, and this will actually show you an address and its symbolic meaning if it does have one, if the debugger is aware of a symbolic meaning. And you can kind of see that this is showing us that this value on the stack is base thread init thunk plus 0x1d. And you can see here's 0x1d on the stack. That is the return value. If we double click on this, you can see this is in the kernel. This is the call which called us. When this call took place, the processor pushed onto the stack this address that you see here, 7F891AA757 or 257D. So that's this. Okay. That's what this address is here. So when we do our ret, the processor is going to pop this off the stack, and it will continue executing code in the kernel after the point at which it made its last call, which its last call is a call to this thunk. What I want to do is I want to just do a T to trace so you can see that this thing pops off the stack. So let's actually look at the stack pointer. Let's actually look at what's on the stack. Let's do a T to run the ret instruction right now. Boom, we run the ret instruction. The red highlighted line in the disassembly window indicates a breakpoint has been set. That's the red highlighted line that is pointed to by the callout line. Ignore that breakpoint. It should not be set at this point in the tutorial. Boom, we run the ret instruction. We've gone back to the kernel to that address that was on the stack. Let's actually look at RSP. We can see that RSP has been incremented by 8. Which makes perfect sense. It's not only 16-byte a line, but more importantly, this address, which was on the stack, which is 8 bytes for this address, this was popped off the stack. It became the current instruction pointer that's executing. Technically, what the processor is doing is it pops that value off the stack and it puts it into the instruction pointer. So that would be RIP. So if we look at RIP, and I don't know if RIP is visible here. I might have to scroll down to find. Here's RIP. So see RIP. So what the processor did is it took this value off the stack and it put it in the RIP register. The RIP register is the instruction pointer register. So you can actually see it here. We do RIP, and there's the value that was on the stack. And if I show you now, RSP has been incremented by 8 because that value was removed by the processor off the stack. So the stack pointer got adjusted up by 8 bytes. And if we do a DPS on the stack, you can see it's now pointing to that location that was just after that address. So here's where the address was. Now it's pointing to this 0. Okay. And so what you can kind of see here is like the processor, you know, it's less of a mystery, right? So the processor has access to a stack. It reaches this, you know, it handles this return instruction. Now that's just an instruction that the processor handles. Well, within the processor, it says, okay, I'm handling the return instruction. So get, you know, whatever value is on the top of the stack and, you know, increment the stack to take that value off the stack, take that value, put it in the instruction pointer, and now start running that code. Well, by putting that value in the instruction pointer, it actually does begin running that code. So it's not like it puts it in there and says run that code. Whatever's in the instruction pointer is the code that's going to be running next. And so that value, that address goes into the instruction pointer, and, you know, that's the next thing that executes is the return is the code that, you know, followed this call instruction in the kernel. Okay, so I want to show something, and this, I don't know if this will be a little too much, but I think it's good to show this. Let me just do this because it's just a way to, what I want to do is I want to grab this address. This is the address. So what I want to do here is this is the address that ends up calling into our main. And I want to set a breakpoint on this after, you know, I restart this process. So let me actually just show you something first. If I type in .restart, it will actually restart the process in the debugger, and I can hit G to go, and we end up in main again. So I can hit G, and there's our message box, and I can click OK. And then I can hit T to trace past that, trace back to the kernel return. So here I am at the point in the kernel. This is the part that called our main function, and this is the return value, the address of the return after the call, which the processor pushes on the stack because of the call. Okay, I want to grab this address right here, and I'm going to right click to copy that address to the clipboard. Now I'm going to put the $ symbol for a comment, and then I'm going to hit enter. So you can kind of see that's the address, right? Now I'm going to do this command called ln, and I'm going to type in the address, and I'm going to hit enter. And you can see that it shows a symbolic name for this particular location right here in the kernel. So if I actually say U for unassemble and that symbolic address, you can see that it is the same call. And this is that point of return that, you know, we talked about here. In other words, this code here is the same as this code that you're seeing in this window here, because this is just the disassembly window, and the U command is just outputting kind of what you see in the disassembly window. What I'm going to do with that is I'm going to hit .restart to restart the process under the debugger. And after we hit restart, I'm going to hit BP and that symbolic address, which I just determined using the ln command. That's going to have us break before main is called. So let me actually set that breakpoint as I did. And now I'm going to hit G. Now that I hit G, you can see that I have hit a breakpoint right here. This is the function. This is the address that we return to, if you recall. And this is the call that calls our main function. Let's kind of see what this does. Now, when you get into thunks and little call dispatching and things like that in the kernel, sometimes there's little tricky things that go on. I'm not going to let me just see what we get into when we trace into this. I haven't looked at this in a while, so I'm not sure what this is going to actually do specifically. So let's trace into it with the T command to trace into it, because I want to see if we can follow it through and I can kind of explain some of it just briefly. So I'm going to hit the T command, which means we're going to call. Now, here's the main thing that I want to show you actually. Let me not forget this. What is our RSP? Our RSP is, so you can see the stack pointer ends in a 0, which means it's 16 byte a line. That's good. And it's at 8D0. Okay. I'm just going to refer to it with a short, kind of name by using the last 3 digits there, 8D0. Let me actually do it's DPS at RSP. So if we do this, we can see that 8D0 points to this 0, right? We don't really care what that is right now. That's just where the stack pointer is. Now, when you do dump commands like DPS or DB, it starts at the low memory address and it dumps downward. In the command window here, it shows, from the lowest address to the highest address. So when you use DPS to dump the stack pointer like this, you're looking at the bottom of the stack at the top there, and you're looking at higher locations in the stack as you look down on this page, because the addresses get higher. So the stack grows downward. So we're expecting that this call function is going to decrement the stack pointer, and it's going to put this number of this address. And in fact, I'm going to right click copy. I'm going to put a comment symbol and hit enter. So you can see that address right here. So there's that address, okay? And what we're going to do is I'm going to hit the T command, and you're going to see what changes here. So first you're going to see RSP is going to change. And in fact, let me scroll up in here. So RSP is going to decrement because the processor pushes the address that's after the call instruction on the stack. So let's do that, right? So here's T. We've done that. Okay, so now we've called into that function, and what we're going to do is look at RSP, and sure enough, it has decremented by 8. It's now, you can see it's now misaligned, meaning it's not on a 16-byte boundary. And that's because, the address is 8 bytes. Yeah, I want to run the, by the way, I'm going to use the up arrow to go to a previous command, and I'm going to recall DPS space at RSP. And then I'm going to hit enter, and you can see now here is that return address, and the stack pointer points right to the return address. Okay, so now we're in this other function, this base thread init xfg, thunk. Well, let's examine what's going on here. It's moving RDX into RAX. So let's actually see ln at RDX. Oh, okay, so it looks like something, Let's actually unassemble RDX. Okay, and it looks like this is going to jump to our program, our main program. Let's actually just verify that by grabbing the address. I think, this symbol would not be there if it weren't accurate, but I, do a little sanity check here by just grabbing the address and doing a U, and we can recognize this right away. This is our assembly code right here. Okay, so what's it going to do? It's going to take RDX and move it into RAX, and now it's loading some kernel, it's loading some address, effective address of some kernel value. Now it's going to jump to some kind of dispatch or call table. So let's actually just go to that. So by the way, everything we've seen so far since that last call instruction, keep in mind that was the last call instruction. So if I look at RSP, it hasn't changed. And if I do DPS at RSP, you can see that here's the stack, here's that return address to the kernel. So nothing has changed with the stack. So this thunk function that we called into, which then jumped to this guard dispatch kind of call function, call pointer table thingy here. That actually, all these jump from one thing to another, but they don't call. So they don't push something on the stack. They're just jumping to a different address. So we have another jump. So I'm going to hit T for trace. So now you'll notice that it jumped to some kind of guard dispatch I call where there's a jump instruction, and the jump instruction is going to jump to whatever's in RAX. And remember, I just disassembled what was in RAX, and we can do it again. If I say U at RAX, you can actually see that it's a little stub that then itself jumps to the main program. So let's actually follow this by doing T. And you can see that this actually jumped to this code right here, which if I hit trace, it's actually going to jump to our main function, which is down below here. Okay. And here you go. You're in the main. So this is our function here, and this is where we call the MessageBox command. So what we noticed is there was this call, and then that call led to a bunch of jumps. It took an RAX value that it got from DX of the caller. So there was a caller from the kernel, that call that we saw, and it had loaded up RDX with the address of some stub that would end up calling our main function. Now, the kernel loader and how it interacts with an executable and how an executable is linked and put together and all these little stubs you see and everything. It's a whole involved thing to get into all of that because, because it's kind of a kernel internals thing. And some of that stuff can actually even change, across different versions of the operating system. But generally speaking, what I'd say to you is if you're looking at stubs like this that call from one thing to another, unless you have a need to examine it for, let's say, security analysis or something like that, if you understand the gist of what's going on, that there's this glue in the kernel that kind of helps connect up what function needs to be called to get the program running, then you can probably ignore some of that stuff unless you really need to dive into it. So I guess what I'm trying to say is in your endeavors with a debugger, looking at the kernel, any of the stuff that you're going to be doing, it's all going to be stuff that, you're going to run into things that you might not need to spend a lot of time on, or you may want to. And it really depends on your context and what you need to do. In this case, what I really wanted to show you here was that there was this call instruction from the kernel effectively into our main, the main entry point of our program. But the way that it worked is it called some kernel func, and that func itself ended up doing some jump instructions, which included a jump to an address within a register value, which kind of indicates that function could probably handle jumping to different parts of the program or in different scenarios, but it happened to be called with an address to a stub that itself could call our main entry point in the executable. And my main reason for showing you this is so that you could see that the last call that occurred was that one that we were focused on. And it is the address after that call instruction that is on the stack, and that's where the ret instruction is going to be returned. So in a sense, what you saw is the kernel called a function and there was jumps, a couple of jumps like this, and then it got to our main program, and then it executed a main program, and then it does a ret, which pops that address off the stack that's over here in the kernel to continue executing. To continue executing. And so the whole point of that is to just kind of show you that sometimes in the kernel, when you're looking at things, you'll see stubs being called and jumps happening and thunks and whatnot. And sometimes at the end of the day, all you need to focus on is, okay, who do we end up calling and where do we end up returning to, or whatever the context is here, right? And we don't have any specific goals with this right now other than kind of familiarize ourselves with the stack space here and, some of these calls and stuff. And it's just a way of doing it. It's a way of taking advantage of this tutorial in order to do this. It's quite a big detour we went down. I didn't really plan on this detour, so I hope you guys are okay with this, and I'm going to try to make sure that I have. Hopefully, if the YouTube table of contents works, you can skip past this if it was too hairy or too long, or you already know about it and you didn't need to see it. Okay, so let's actually go back to our program. So now we're at this program, and what we see here is that we set up the stack properly as we're supposed to, which is to fix it to be 16-byte aligned as part of our prolog's duties. It's supposed to do that. And then we want to add 32 bytes of shadow space for the upcoming call that we're going to make. So when we call the function, we're 16-byte aligned and we have shadow space. The processor is going to put our return instruction on the stack, and it's going to call the MessageBox function. When the user clicks OK, it's going to come back to us. Now, what we can do is we can actually restart this. Now, this was from the prior section, so if you didn't follow that section, that's okay. We're just going to restart this. We're actually going to run this code. This is sort of the faster path. So if you skipped ahead here, that's totally okay. So I'm going to hit G to run this, and now we are in the function. It's in our main function, and we're going to trace past this RSP sub RSP minus 28. So when we sub RSP minus 28, we are preparing shadow space for the upcoming call, as well as aligning the stack to a 16-byte boundary before we exit our prologue. And our prologue really consists of this one line, this sub RSP minus 28. Now I'm going to go and trace past these things. We're going to 0 RCX. We're going to load into RDX. We're going to load that first string. We're going to load the title bar string. So we have the message box string. So I'm going to do dump ASCII, or actually we could do dump byte and say RDX and dump byte, and R8 is that third parameter. And you can see that here are the strings that we're passing to the MessageBox function. Then we are going to trace past this. That zeroes out R90, which is the MBOK. And what we're going to do is I'm going to show you. So here is RSP, and I'm going to do DPS RSP. And you can see here's that kernel return address. Here's the shadow space that we allocated. Here's the extra 8 bytes to realign the stack on a 16-byte boundary. What's going to happen now when we do T to trace into this call is actually going to have the processor push our return address on the stack, this one that comes right after. So that's the one that ends with 102D. So we're going to see that on the stack. Let's actually do T. And here we are in the MessageBox API in user 32. Let's actually look at RSP. And so RSP now has D8, CD8. Before it had CE0. So it has the return address on the stack there. We can actually do DPS. So I'm doing up arrow now to recall the previous command of DPS RSP. And we can see this is our return address, this one right here. And if I actually do Control G to go to that return address, you can actually see that it highlights the address after the call. So it's kind of like the same thing as that one when the kernel calls us. There's sort of a pattern here. I'm going to double click in the stack pane here on MessageBox A. And what do you notice here inside MessageBox A? You see a sub RSP, 38 hex. So we see the extra 8 bytes there at the end there, that 8 bytes. That 8 bytes is actually going to realign the stack on a 16-byte boundary. So that extra stack space, that 30, could be for shadow space for upcoming calls, as well as local variables that the MessageBox A function has. So what I'm going to do here is I'm going to do the GU command. The GU command is going to finish running the function that I'm currently in, and then it's going to stop when it exits out back to the callee or the caller function, which is our main function. So if I do GU, well, GU is going to stop here because it's going to actually prompt me, but when I click this, the GU command finishes executing, and it finishes outside the call to MessageBox A. Okay, so that's pretty much it for that. I just hit G there to end the program, and it terminated the process. I'm going to exit the debugger here. And what I'm going to do here is I am actually going to remove all this. And what I wanted to do was I wanted to comment out the shadow space stuff here. And I want to show you what happens if we don't set that up properly, right? So I'm going to run this. And I'm going to go in the debugger. And I'm going to go and run this. And you can see we got an access violation inside of MessageBox. So here's our main function. And you can see our main function no longer has the proper setup for the stack. So it ended up calling this function with the wrong kind of alignment, not 16-byte alignment. And so there was no natural misalignment. So when MessageBox A did all of its subtraction to fix up the stack, it actually ends up not fixing it up properly. We also don't have the scratch space there, the shadow space that we're supposed to have there before we call. So we didn't call the function with the right calling convention by not including those instructions that I just commented out, and we got an access violation, which is a crash basically. And we can actually see that. I mean, if I just run this directly now, our program, and I run it, you can see it prompts me with the debugger because I have just-in-time debugging enabled. So it prompted me, it's saying, hey, there was an unintended, an unhandled exception, and do you want to debug this, right? So let's put this back to normal, and we can actually build this. And we can actually run it, just make sure it works, and it works great. And we can make sure our exit code should be good. Yeah, there we go. Hey everybody, quick insert here. I wanted to actually show something here regarding the tool now that we've finished the program and everything. So you see that this is our command line here that we've been running to build our program, right? And so now our program is built and we can run it and we get the little prompt. Okay, everything's great there. Now let's add something to the assemble command that was pretty common actually back in the day when assembly was very popular, and you might be running a tool like this quite often. What you might very often do is add a switch like this. So actually, let me actually put a comment here for a second so I can actually show you the documentation for that switch. So if you go here, you can see FL is to generate a listing. That would be an assembly listing. And so if we go here and we do the same command we did before, but we actually include FL/F, capital F, lowercase l, that will instruct the assembler to generate an assembly listing. So let's generate the listing, and there it goes. It looks like it's pretty much the same output as when it's doing a normal assemble. But if we look in the folder here, we can see that it generated an LST file. Let's go ahead and load that in VSCode. Okay, after we load this in VSCode, and we can actually widen this up here. You can actually see this is an assembly listing. Like back in the day, people would write entire programs out of assembly. I mean, games might be written out of assembly, even utilities and things like that. I mean, if you go back to like CPM days or even early DOS days, a lot of tools were written in assembly for economy, and simply that was the best tool to use for the kind of economy you could achieve for lots of different reasons. One is to keep programs small so you could fit them on disks rather than several disks. That might be one example. Another example is obviously speed and performance. You could actually hand optimize, which, you could do a much better job than any kind of compiler back in those days. And you could do all kinds of tricks. You could use registers in ways that, maybe a compiler wouldn't use them. Today, optimization is quite, fantastic. But back decades ago, it really wasn't. And so hand rolling assembly was something you'd really want to do. And I would even say today, it's still an important skill to be able to have for certain kinds of embedded systems. You might have a choice of languages, but you might be able to get finer control by just going directly to the processor with assembly or as close as possible. And so like in the days of CPM and MS-DOS and even early Windows and things like that, if you created entire programs from assembly language, you might generate an assembly listing, and you might actually make notes in the assembly listing and scratch things off or draw lines, and you might have some bug you're tracking down. So you might look at the assembly listing to ensure that you look at everything very carefully, and you can actually see the bytes and everything. And if you look, you can kind of see it shows like the data. Here's our constant data that we defined, and it shows you like the segments and stuff. It actually shows you the bytes as well. So it's showing you the assembly language, right, along with what bytes it ended up creating from that assembly language. You can see it does the same for the program. So here it's showing the program offset. This is an offset that would actually be relative to whatever the base address is, wherever this code is going to reside. And you can see here's our assembly language, but it's also showing the machine code, and our comments are left in line here. And it just kind of shows you everything in here. And what you could do is you could go down the listing and look at everything. I mean, you might be trying to track down a bug where you're jumping somewhere and you're calculating an offset as to where to jump, and maybe it's getting hung up, and you look at the listing and you can kind of see like, oh, I'm jumping here, I'm doing this calculation wrong or something like that. But assembly listings are still very popular in a sense, vis-a-vis tools like Ghidra and even debuggers. In a sense, that format for a disassembly listing, it follows a little bit like the assembly listing that you'll get when you assemble, like what we just showed right here. So there are roots in a sense with a lot of the things we see today in debuggers in Ghidra. Some of those roots go back to, DOS days, early Windows days, CPM days, kind of back in those early PC or microcomputer days where they had tools a lot of tools that might have been written and even built in assembly language on the system. Like if you worked with CP/M, it wouldn't be uncommon for you to download source code for, some tool like an editor or something like that, where you would actually compile it or build it. Some of these assembler listings and the formats you see in Ghidra and semicolons at the end of the line to indicate a comment, and things like db for defined byte, which you see here, db, and some of the byte dumps that you see here, even though they may look a little different in some of the tooling like the debuggers or Ghidra or whatnot, there are roots to the past in some of that formatting. Not so much to spend tons of time, studying, macro assembler or whatnot. By diving in, we got a chance to kind of look at that, but we also got a chance to touch on some things with the debugger and whatnot that are relevant for today's world. So I hope you found all that connection, it was a little bit organic as we were jumping around here to different things. I hope you found it helpful though. All right, everybody, that's it for this video. If you liked it, I hope you'll click like, and if you want to subscribe, that would be awesome. If you have some experiences trying this out, comments or whatever, I hope you'll leave them down below in the comments section, have some discussion down there. Other than that, wishing you a very successful Happy New Year 2024. Big thumbs up to you guys. Much success to you in 2024. Rock it out, all that jazz. And until the next video, be well, be safe, all that jazz. All right, everybody, take care. Thanks. Bye-bye.